Welcome to the course of Internet Protocol version 6. So in this course we will discuss about the various aspects of the IPv6, and here we will start our course with very basic terms and goes over to the advanced level. So in today's class we are going to discuss about the brief introduction to IPv4. So before IPv6 we are on the IPv4 addresses. So before discussing about the IPv6 we have to discuss brief terms of the IPv4 addresses. So let's start with here we will discuss about its address type, notation, IPv4 packet format and the NAT process. So starting with the first, what is the IPv4 address? So here IPv4 stands for the Internet Protocol version 4. So it is the fourth version of the IP addresses, and before IPv6 we are using these IPv4 addresses to give the identification to a device in a network. So it is a connectionless protocol that is used in a packet switch network such as the internet. And here the IPv4 is designed and specified in IETF, that is Internet Engineering Task Force publication, that is RFC 791. So it provides the logical connection between the network devices by providing authentication to each device. So these IP addresses act as the identification to a devices in a network. Next is address type. So here the address space is the total number of addresses used by the protocol. So here the IPv4 is a 32-bit address, which means it consists of 2 raised to power 32 address space. And the example here I have given of IPv4 address, it is written as 117.149.29.2. So this is the decimal notation of the IPv4 address. So here this 2 raised to power 32 address space means there are total of 4 billion devices that can be connected to internet by using the IPv4 address. But due to some imposed restriction, like we have classified these IPv4 addresses into different classes like class A, class B, class C, class G and class E. So as they are classified, so we have imposed some of the restriction to these IP addresses. So the actual number that are available in IPv4 address space are much less than 4 billion. So next we will discuss about the notation. So here the IPv4 address can be represented into two ways. The first one is the binary notation and second one is the dotted decimal notation. So the binary notation, here we will use 32-bit address in which there are 4 octets each having the bytes. So here the 4 octets are like first, second, third and fourth. So these are separated by the dot. So this yellow color 0 and 1 bits represents the binary notation, and these total consist of 32 bits. And dotted decimal notation, here the each number in dotted decimal notation value ranges from 0 to 255. So here we have represented 172.16.150.12 in decimal notation. So here this decimal notation is converted into the binary. So this is the binary form of this particular address. So here dotted decimal notation, IPv4 address are written in decimal notation to make it more compact and easier to read. So most of the time we will use this decimal notation to represent the IPv4 addresses. Next is the header of the IPv4. So this is the packet format of IPv4 addresses. It consists of IP header and the payload data. So here the IP header will consist of the source address, destination address, the header length, the next header. So these are the information that are added in this IP header. But in this payload data, it will contain the original data of the users. So here the IP address is of 20 to 60 byte long, and here is this total IPv4 packet format is of 65,535 byte long. Next is the IPv4 header. So here IPv4 header have many fields in between. So it starts with the version, header length, TOS, total length, identifiers, flag, and then the fragment offset. And we have added the TTL, protocol header checksum, and it will contain the source address and destination address with option and padding. So this total header size is of 32 bit. Let's discuss about these one by one. The first one is the version. So here the version will indicate that the 4-bit field is set to binary 0100 for the IPv4, and if it contains the value like 0110, then it means this is a IPv6 packet. So here this first field of IPv4 packet will tell about the version of the packet format. Then part is the header length. So here header length is also known as the internet header length, and it is the second field of the IPv4 header, and it consists of 4-bit long. So it tells the number of 32-bit words in the header. It means it is telling the total length of the header part only, and the minimum value of this field is 5. Next part is the type of service. Type of service, that is TOS. So here it is also known as differentiated service code point, and it is of 5-bit long. And here it tells the real-time data streaming applications such as VoIP. It will use in this process. So here it carries the information about the quality of service of the IPv4 packet. So after that, the next part is the total length. Total length field is used to define the length of the entire IP packet. So as header length is only defining the length of the header part, but total length is defining the length of the complete IP packet. Next is explicit congestion notification. So here this ECN carries the information about the congestion seen in the route. So this is 1-bit long, and it allows end-to-end notification of network congestion without dropping. After that, the next part is the identifiers. So here identifiers, the identification field is used for uniquely identifying fragment of an original IP packet. So it used for adding packet tracing information to help trace datagram with spoofed source addresses. Next is the fragment offset. This fragment offset field is 13-bit long, and it will this offset tells the exact position of the fragment in the original IP packet. Next part is the protocol. So here it indicates the protocol that are used in the data portion of the IP packet, that it is consisting of ICMP protocol, TCP protocol, or UDP protocol. If it is ICMP, then the value for this protocol is 1, protocol field is 1, and if it is TCP, then the protocol field value is 6, and if it is UDP, then the protocol field value is 17. After that, the checksum, header checksum. Header checksum are basically used for the error checking of the header, and it is of 16-bit long. And source address indicate the IP address of the source of the packet or the generator of the packet, and whereas destination address is the receiver of the packet. It will include the address of the receiver who is going to receive the packet. Next is the flag. So here the flag, there are 3 bits field that are used to control and identify fragment. The first one is bit 0. If it is set to 0, it means it is resolved bit, and there is no fragmentation is done. After that, bit 1 indicate that there is no fragmentation, and it is indicated as DF. Bit 2, it will indicate that there is more fragments, and it is indicated as MF. Next part is time to live field, TTL field. It indicates the maximum time for which a packet is allowed to remain in an internet system. So here the intention is to cause undesirable packet to be discarded. So the maximum datagram lifetime is range from 0 to 255, and it is 8-bit long. The option field here, it is used for the it is reserved for the future use, so that's why this is an optional field in IPv4 packet format. So these are the various fields that are in between the IPv4 header part. The next is the NAT process. So here the NAT stands for network address translation or network address translator. So it is a virtualization of internet protocol addresses. So network address translation is a process where a network device like a firewall assign a public address to a computer inside a private network. So in NAT, there are the private addresses ranges used like class A, class B, and class C. So class A addresses are 10.0.0.0 to 10.255.255.255. Next, The class B addresses are 172.16.0.02, 172.31.255.255, and the last one class C that are mostly used, that is 192.168.0.02, 192.168.255.255. So this help in improving security and decrease the need of large number of IP addresses in our organization. So this is a very helpful process, that is network address translation process. So here how this technique will work. So here the NAT technique work well for computer that only have to access resource inside the network. So like we are designing a network, and in network we have a few number of computers or laptops. So we want to that these computers and laptops must share the information with each other. So we are designing one private network. So for example, host want to access file server or the printer. For that we also use this NAT process. Thus using private address router inside the private network can route traffic between the private address with no trouble. But if a host want to access the resource, like if that devices want to access the outside network like the internet, then host must have a public IP address. So here in this way NAT address translation work. So this diagram shows the description of network address translation. Like here I have designed a network with these three computers having an address of class A, that is 10.0.0.2, 10.0.03 and 10.0.0.4, and this is a NAT router having a two port. So to one interface we have given an address 10.0.0.1, and to another interface we have given 145.12.131.7. so these are the private IP address, whereas this is a public IP address. So here what we are doing here, if these computers want to communicate in between the network, they will route the packet by using their private IP addresses. But if they want to access anything from outside the network, they have to use their public IP address to be used for the external network. So if in case any of the device from the internet want to access or want to send message to these devices in the private IP address or private network, what happen, it will use this address and the message will receive by this, and after this it will send the message to these devices in the private network. So it means in public IP, in external network we are only known by this public IP address, whereas in the private network we are only known by this particular address. So this is a NAT process where we are using private IP addresses and public IP addresses to differentiate the internal and external network. So this is all about the brief introduction to IPv4 and with NAT process. Thank you. To the course of IPv6. So today we are going to discuss about the introduction to IPv6. So as in previous lecture we have discussed about the IPv4 addresses. So in this class we are going to discuss about the brief introduction to the IPv6. So in this class we will discuss about its feature of IPv6 and why we need this IPv6 addresses and its advantages. So starting with the first, that is IPv6. So what is IPv6? IPv6 are the network layer protocol that provides the identification and location of computers on network and routes the traffic across the internet. It means it works same as that the IPv4 addresses that are also used for giving the identification to the network addresses and network devices. Same way here IPv6 is used to give the identification and tracing the location of the devices over the network. So IPv6 is also introduced by IETF, that is Internet Engineering Task Force. So IPv6 is also known as IPNG, that is Internet Protocol Next Generation, and it is the most recent version of the Internet Protocol. So it was introduced to replace the widely used IPv4 address that is considered as the backbone of the modern Internet. So in 2004, Japan and Korea was first in public deployment of IPv6. So now we are using these IPv6 addresses in our devices and today's. Next, is the features of IPv6. So the first feature of IPv6 is about the source and destination addresses. So it is 128-bit long. It means as in IPv4 the source and destination addresses are of 32-bit long, here these addresses are of 128-bit long. Next one is the simplified address header by moving all unnecessary information. So by removing the unwanted information from the IPv4 header, we have made the IPv6 header simplified. So as in IPv4 header, we have discussed about lots of fields that are included in IPv4 header. But as in coming lecture we will discuss about the IPv6 header, we will see that IPv6 header is very simplified header, having very by removing all unwanted information that we don't want to use in the IPv6. Next part is it provides end-to-end connectivity. It means it is providing the IP addresses to each device in the network, and it makes the communication through the internet without using the net. So here we are not using the net technology. Here we are providing the every device in the internet with a particular IPv6 address. It is a faster forwarding routing due to the less detail at the header. As we have made the header part simpler, it will make the faster forwarding and routing communication in the IPv6 by using the IPv6 packets. It has IP security which make it more secure than the IPv4. So in IPv6 address we have added a new field of IP security, so it will add a more security to the IPv6 packet. And it uses multicast to communicate with the multiple hosts. So here we are using the multicast mode of addressing an IPv6, and it is used to communicate with the multiple hosts at the same time. So here in IPv6 it doesn't support the broadcast addressing, whereas in IPv4 it supports the broadcasting addresses, but in IPv6 we will discuss about the unicast, multicast and anycast addresses. Next is anycast mode for packet routing is introduced. So there is a new part that is added over here, that is the anycast mode of addressing. We will discuss about this later on. So next it enables hosts to roam in different geographical area and remain connected to the same IP address. It means the same IP address our devices have a same IP address irrespective of the location. So if we are locating ourselves in the new geographical area, the IP address will remain same in IPv6 packet format. Next is it uses 6-bit DHCP and 2-bit ECN to provide better quality of service. It means here as in IPv4 we have used less number of bits for DHCP and ECN. So to enhance the quality of service information, here we have used the DHCP and ECN bits more, that is 6-bit DHCP, the referential service code point, and the ECN is the explicit congestion notification, and it is of 2-bit. Then it supports smooth transition. It means transition from IPv4 to the IPv6 addresses. Like a source is using the IPv4 address and it wants to send the information to a device that is using the IPv6 address. So due to the combination of these IPv4 and IPv6, we have to make the smooth transition between these addresses. So here it supports the smooth transition. So these are the features of the IPv6. Next is why we need IPv6 IP addresses, as we have the IPv4 addresses, a lot of IPv4 addresses. So the reason being is to make communication possible, every device need a IP address to make it connected to the internet. So here the internet address system decided that IPv4 had a capacity of 4.2 billion addresses. As it has a larger capacity of 4/2 billion addresses, so the problem arises when the number of devices in the network increases. So as the number of devices in network increases, like a computer, smartphone, TV, smartwatches, cars, so these all are using the internet. Due to the evolution of internet over things, that IoT, due to which the increase in number of devices over the internet is increased. So these addresses are not enough to meet the demand of the new devices. So these 4.2 billion addresses not meet the demand of the enough number of new devices. So to meet the demand, to overcome the shortage of IPv4 addresses, many methods are used to prevent the depletion of these addresses. Like we have used the subnetting, where we make the subnet of the particular address, VLSM, NAT, and these methods are no longer able to provide IP addresses to the network for the future demand. So to make the future demand possible, we have used the IPv6 addresses. So here we have represent the numerical representation of these IPv4 and IPv6 address. As IPv4 addresses have 32-bit address, it means it has 2 raised to power 32 IP addresses that equates to the 4.2 billion addresses. So to overcome the limitation of IPv4, we use the IPv6 addresses. So IPv6 addresses are 128-bit long. That means they are 4 times larger than the IPv4 addresses. So 2 raised to power 128 means the total IP addresses are 340 trillion IP addresses. So thus this is the reason with the deployment of IPv6 address. So this is the very big reason to deploy the IPv6 addresses in the network to meet the future demand. The next is the advantages of IPv6. So the advantages of IPv6, first one is the larger address space. It means as we are using 128-bit long source and destination addresses, that means it has a larger address space. Next one is better header format. Better header format means it as we have removed the unwanted information from the header, it make it simpler and better. Next is new additional option. New additional option, as we have used the IP security, the extension header. So these are the additional information that we added in the IPv6 packet. Next is allowance for the extension. As here in this we are using the extension header to add the additional information like hop by hop option, destination options, routing headers. So due to this provide of this extension header in the IPv6 packet, it make us to add the additional information if it required. Next is more security. So due to the adding of IP security field, and this it enhance the security of the IPv6 packet as compared to the IP4 packet. So this is all about introduction to IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the IPv6 protocol structure. So in this class we are going to discuss about the topics like the IPv6 address structure, the rules of address notation, and the packet format. So starting with the first, that is the address structure. So how to write the IPv6 addresses. So as the IPv6 addresses are of 128-bit long, so it is divided into 8 16-bits block. So each block is then converted into 4 digits. So it is represented by hexadecimal number represented by the colon symbol or separated by the colon symbol. So this IPv6 addressing structure is designed in RFC 4291. So let's discuss the representation of this. So for example, here I have taken the example of the IPv6 address that is represented in binary format. So here the binary format is divided into 8 16 bits block. So here you can see that there are 8 blocks, 1, 2, 3, this one is the 4th, 5th, 6th, 7 and 8. So these are the 8 blocks, and in each 8 block we have 16 bits. So these 16 bits represents this particular IPv6 address that is represented in hexadecimal format. So each block is then converted into hexadecimal and separated by the symbol. So it represents the 2001 colon 0000 colon 3238 colon DFE1 colon 0063 colon 0000 colon and 0000 colon then FEFB. So this is the IPv6 address that is 128-bit long, and this is the binary notation, and this here this one is the hexadecimal notation. Coming to the next part, how to write these IPv6 addresses. So IPv6 addresses has some rules to shorten these addresses. So discard some zeros or to add some information. So like the first one rule is discard leading zero. So if we discard the leading zeros, so like here I have represented leading zeros of a section can be omitted. Only leading zeros can be dropped, no trailing zeros, such as in block 5. So here we have to only drop the leading zeros. Like in block 5, we have represented these zeros 0063, and here I have in next we can drop these zeros that are the leading zeros, but we can't drop the zeros that are coming in between or that are coming after that are the trailing zeros. So the first rule is discards the leading zeros to make this IPv6 address short. Next rule is replace consecutive zero. So to replace this zero, if two or more blocks contain the series of zeros, then omit them all and replace it with the double colon sign, and such as in this 6th and 7th block. So here in this IP addresses, here we have represent these series of zeros that come in between the IPv6 address. So we can omit it and it represented with this double colon. So this will make this IPv6 address more short. Next rule is the consecutive block of zeros can be replaced only once. So if there are still block of zeros in the address, they can be replaced by a single zero, such as in the second block. So like here we have represented as a series of blocks are converted into the colon to make this IPv6 address short. So if more zeros are come in between the address, we can't use the colon again, double colon again. Here we have to represent this zero by the single zero. So these are the rules to represent the IPv6 address. Next is the how to represent the IPv6 and IPv4 address together. As our network has a combination of these two addresses, so how to represent these two addresses together. So the format of IPv6 addresses is we can represent the IPv6 address in the Y format, and the X represents the IPv4 addresses. So it can be written as 2001 colon db8 colon 3333 colon 4444 colon 5555 colon 6666 colon, and then the IPv4 address, that is 192.168.1.4. So here the IPv6 represents in the segments, and here it represented in the hexadecimal number from 0 to FFFF. And where IPv4 addresses are represented in octet format and the decimal number that are ranging from 0 to 255. So in IPv6 it are separated by the colon, and IPv4 addresses are separated by the period or the dot sign. Next is representing these addresses together. So IP address, I want to represent the IP address 192.168.0.2 into this combination of address. So method 1, I can write it as 0 colon 0 colon 0 colon 0 0 0 then 192.168.0.2. The another method is I can represent the double colon in front of this IPv4 address and then 192.168.0.2. Then the another method is hexadecimal representation, in which I convert this IPv4 address into the hexadecimal format. So it is represented as double colon CO8 colon 2. So this is the representation of the IPv4 and IPv6 address together. The next we are going to discuss about the structure of IPv6 packet. So the IPv6 packet is consists of IPv6 header, extension header, and the upper layer protocol data. So IPv6 header contain the information, the basic information like the source address, the destination address, the header length, etc. Whereas the extension header will contain the extension additional information like the hop by hop option, destination option, router header, etc. And here in upper layer protocol data, here the information of the user is added over here in this block, upper layer protocol data. Let's discuss about the IPv6 header. So the IPv6 header is consists of these particular fields like version, traffic class, flow label, payload length, next header, and it is of 32-bit long. So you can see from here the IPv6 headers is more complex than the IPv4 header, as IPv4 header consists of a number of fields. Here the number of fields are less. So let's discuss about these fields one by one. The first one is the version field, that is 4-bit long, and it is same as the IPv4, but it is represented by this bit sequence with 0, 1, 1, 0. So this particular version field will remain constant. The next part is traffic class. Traffic class is it of 8-bit long, and this field has the two values, that is DS and ECN. So here this field, these 6 most significant bits are used for differentiated service, and the remaining 2 bits are used for the ECN, that is explicit congestion notification. So these traffic class represent these 2 different bits. So DS classify packet, it is end up with 0 bit and it is a standard bit. If it is end up with the 1 bit, then it is a local or a experimental use. So ECN is representing the 2 part, that is congestion control traffic or no congestion control traffic. The next part is the flow label. Flow label is used for giving real-time application service and also used to detect the spoofed packet, and it is of 20-bit long. So the size of the next part is the payload length. So the payload length here represents a hop by hop extension header. So whenever a hop by hop extension header holds a jumbo payload option, then the length is set to 0. Here the jumbo payload is a user data field that exceeds the IPv4 limit of 65,535 octet is called the jumbo payload. So if it exceeds this, then we have to add the hop by hop extension, and here the length is set to 0, that is, and so this field is of 16-bit. The size of payload length is represented in octet by including extension headers. The next field is the next header field. So next header field specify the type of next header, and it is of 8-bit long. This field usually specify the transport layer protocol used by the packet payload. Next is hop limit. Hop limit is specify how many number of devices can be visited by a packet. This field replaces the time to live field in IPv4. So this particular field works same as the time to live field and IPv4, and it is of 8-bit long. So the value of this field decreases by 1 at each intermediate node visited by the packet. When the counter reaches 0, the packet is discarded. So in this way, this hop limit counts. Next is source address and the destination address field. Source address contains the IP address of the source node, that is the originator of the packet, and it is of 128-bit long. And destination address indicates the IP address of the node where we want to send our IPv6 packet. So this is 128-bit long. So this is all about the IPv6 structure part. So thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the extension header and the prefix notation in IPv6. So as in previous class we have discussed about the IPv6 header. So in this class we are going to discuss about the extension headers and its prefix notation. So let's first start with the extension headers. So here the extension headers are added to IP packets to give them a greater functionality. So it is added with a base header, and these are the extension headers that we can add to the IP address, like hop by hop option, source routing, fragmentation, authentication, encapsulating security payload, and the destination option. So let's start with discussing about this one by one. The first one is hop by hop option. So here the hop by hop option specifies delivery parameters at each hop on the path to the destination host. It means it is telling the destination host about the number of routers that are visited by the packet as they are traveling from source to the destination. So they are giving about the information about all the routers that is visited by the packet. So it is identified by the value 0 in IPv6 header next header field. It means if the next header field have the value 0, then it means it has extension header known as hop by hop option, and it is of 8 byte long. Next part is destination option. So here the destination option header has the value of 60 in header's next header field. It means if the next header fields contain the value 60, then it will defining the destination option with as the extension header. So it is used to specify packet delivery parameters for either intermediate nodes or the final destination. So here it also defining the packet delivery parameters like the source address or the destination address and the number of hop count. So it is delivering all the packet information to the intermediate node as well as to the final destination. Next we are going to discuss about the source routing. So here the source routing header have the value 43. So here if the next header fields have the value 43, then it is adding a source routing as extension header. So it specifies a source route which is consisting of intermediate nodes travel by packet on its path to the final destination. So here the source route is specifying the number of intermediate nodes that is traveled by the packet from source to the destination. And next header is fragmentation header. So here the fragmentation header is used for IPv6 fragmentation and reassembling services. If the value of next header field is 44, then it means the extension header is the fragmentation header that is added with the IPv6 packet. So fragmentation header is used when a packet to be sent is larger than the maximum transmission unit a data path can hold. So here then the sending node splits the packet into the fragmentation. So the packets are splitted into the small groups, and the fragmentation extension header carries the information that is necessary to reassemble the original packet at the destination node. So these are the functions that is performed by the fragmentation header. By first of all, it will fragment the packets into small groups, and then it will pass the information to the destination how to reassemble these small groups into a original packet. Next is authentication header. So here the authentication headers is added when the value of next header field is 51. So here authentication headers contain information that is used to verify the authenticity of the packet. So it provides data authentication, that is verification of the node that sends the packet. Data integrity, that is the verification that the packet was not modified while transmission. And anti-relay protection, that means the assurance that captured packets cannot be retransmitted and accepted as a valid data for IPv6 packet. So these are the functions that is performed by the authentication header, that is data authenticity, data integrity, and the anti-relay protection. The next is encapsulating security payload. So here it contains the information used to verify the confidentiality of the packet. So it means here it provides data confidentiality, data authentication, data integration, and the replay protection services to the encapsulated payload. And if the value of the next header field is 50, then it will contain the information about the encapsulated security payload as extension header. So this is all about the extension header that we can add to the IPv6 base IPv6 header. Next is prefix notation. So what is prefix notation? The prefix notation is a length or a prefix length that is a decimal value indicating the number of leftmost contiguous bit of the address. So here, like the prefix length is in IPv6 is expressed as an integer between 1 to 128. So here the example like 2001 colon db8 colon abcd colon 0012 double colon 0 has the prefix length that is /64. So here the /64 is giving the information about the prefix notation, and it specifies a subnet with a range of IP addresses from 000 to FFFF. So these are the range in between this particular IP address. So it represented by using the following format, like we will write the IPv6 address first, then we will write the prefix length. So as I have written here, first of all I have write the IPv6 address, then its prefix notation. So here the bold part, that is this, the portion in the bold is the network portion, whereas this part that is non-bold is defining the host portion, and it will identify an individual host on the network. So these values will goes on increasing and it will reach to the FFFF when we will define in the network. So this is about the prefix notation. Next we will discuss about the IPv6 address consists of network address, subnet address and the device address. So these are the part of the IPv6 address. So network address are the first three grouping of numbers in the subnet mask, and these are the first 48 bits that will represent the network address. Then is subnet address. Here the fourth grouping of number in the subnet mask is the subnet address. That means the bit from 49th through 64 bits are the subnet address, whereas device addresses are the last four grouping of number in the subnet mask make the device address, that is the last 64 bits. So let's see how these are divided over the IPv6 address. So for example, the first three representing grouping of three representing the network address, that is 48 bits, then 16 bits will represent the subnet address, and after that the last 64 is representing the device address. So device address will change as on in the network, and if we are defining this address in a particular network, then it will the network address as well as the subnet address will remain same, but the device address will goes on change. The network address and the subnet address combine together to make the IPv6 prefix. So network address can also be known as routing prefix, subnet address can also be known as subnet ID, and device addresses can also be known as interface identifier. So these are the part of the IPv6 address. So this is all about the extension header and the prefix notation in IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the difference between IPv4 and IPv6 backend addresses. So here in this class we will discuss about the difference between the IPv4 and IPv6 and their header difference. So starting with first, that is comparison of IPv4 and IPv6. So IPv4, it is of the address length of this is 32 bit, that means 4 bytes, and the address length of IPv6 is 128 bits, that is 16 bytes. So here in IPv4, header includes a checksum and the option field, but in IPv6 checksum is not included in header and it is added in the optional data as the extension header. Then the fragmentation is performed by router and sending host in IPv4, but fragmentation is only done by the sending host, and it is this information is added in the extension header in IPv6. Next part is the IGMP is used to manage local subnet group level. Here in this IPv6, the IGMP is replaced by the multicast listener discovery messages, that is MLD. Next part is the these IPv4 addresses are configured manually or through the DHCP, but IPv6 doesn't require manual configuration or the DHCP configuration. So IPv4 address support the 576 byte packet size that are fragmented, and IPv6 support the 1280 bytes of packet size that are not fragmented. It means the IPv4 having a packet size of 576 byte and IPv6 can support 1280 bytes of packet. Next is IPv4 doesn't support the IP security and it is in optional field, whereas IPv6 has the end-to-end IP security support that is the mandatory for the IPv6 packet. And IPv4 ICMP router discovery is used, whereas in IPv6 ICMPv6 router solicitation and the router advertisement messages are used. Coming to the next part, that is the comparison between the IPv4 and IPv6 header. So in IPv4 we are using the version with the binary value as 0100. In an IPv6 the version field have the binary value of 0110, and the second part, it contains the internet header length, whereas in IPv6 it is not specified because the header length is of fixed size, that is 40 bytes. In IPv4 we have used the type of service, whereas in IPv6 it is replaced by the traffic class field. And IPv4 we are using total length, whereas it is replaced by the IPv6 payload length field in IPv6 packet. IPv4 packet use the identification, and in IPv6 we are not using this field and it is removed from the IPv6 packet. IPv4 packet have the option format, and an IPv6 packet it removes in the IPv6 and it adds on to the extension header. Next is fragmentation flag. Fragment offsets are used in IPv4, whereas IPv6 doesn't include these, and these fragmentation information is included into the extension header. Next part is time to live field. So in IPv4 have a time to live field, and here in IPv6 it is replaced by the hop limit field. IPv4 have information about the protocol that we are going to use in the packet, but IPv6 is replaced this as a IPv6 next header field. IPv4 header checksum is used and it is removed in the IPv6 packet. So then is source address and destination address are there in IPv4 as well as in IPv6, and in IPv4 it is of 32-bit long and in IPv6 it is of 128-bit long. So this is the comparison between the IPv4 and IPv6 and the IPv4 and IPv6 header. So this is all about the comparison of IPv4 and IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the type of addresses in IPv6 packet. So in this class we will discuss about these type of addresses. So the type of network communication in IPv6 are of unicast address, multicast address and the anycast addresses. Here we are not using the broadcast addresses. Let's discuss about this one by one. The first one is the unicast address. So the unicast is a type of communication where data is sent from one computer and it is received by the another computer. So it means it is one by one communication. So a unicast address uniquely identify an interface of an IPv6 node. The example of IPv6 unicast type of network communication is like browsing a website, downloading a file from a FTP server. So these are the one by one communication. These are done by the using the unicast addresses. It means single addresses that representing the two different devices, that is the source device and the destination device. Next is multicast address. Multicast is a type of communication where data is sent to a group of devices in the network. So multicast address identify a group of IPv6 interfaces or the addresses. So IPv6 multicast data is sent to a group and only member of that group receives the multicast data. For example, the online TV. So this is the example of multicast addresses. In multicast addresses, there is a one sender and there is a group of receiver that receives the particular data. Next is the anycast address. So this is the additional option in the IPv6 that is not represented in the IPv4 packets. So anycast address is assigned to multiple interface. So in anycast, the packets are routed to the nearest devices or the IP address or the interface from a group. So for example, it is used in content delivery network CDN. So as in anycast, it is having a similar type of multicast addresses, like if there is a one sender and a group of devices are there that act as the destination, but in anycast it will send the information to the nearest device first and then it is routed to the another nearest device. But as in multicast, the same information is simultaneously sent to the number of users that are present in the group. But here the anycast will send the information to the nearest device first and then to the another hop. So these are the difference between the multicast and anycast. So these are the type of IPv6 addresses. So thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the IPv6 unicast address. So as in previous lecture we have discussed about the type of addresses in IPv6. So in this class now we are going to discuss about those addresses one by one. So starting with the first address, that is the unicast address. So in this lecture I am going to discuss about the type of unicast addresses and its address scope. So starting with the type of addresses. So first of all, what is the unicast address? So unicast addresses are the addresses that are given to a particular source and destination addresses. It means this is a one-by-one communication. There is a single address to the source and the single address is given to the destination, and they have a communication in between the sender and the receiver. So that is the unicast addresses that are given to the source and the destination address. So now the type of IPv6 unicast addresses are, first one is global unicast address, the second one is link local address, third unique local addresses, and fourth one is the special addresses, and fifth one last is the embedded IPv4 addresses. So let's discuss about these types of unicast addresses. So first one is the global unicast addresses. So IPv6 global unicast addresses are similar to that of IPv4 public IP addresses. So these, as IPv4 public IPv4 addresses are assigned by INA, same way these global unicast addresses are assigned by INA, and it is used on a public network. So here these global unicast addresses have a prefix of 2000 double colon, and it has a prefix notation as /3, and in binary representation of this particular prefix is given as 001 in the packet format. So these are the few points about the global unicast addresses. After that, these global unicast addresses are divided into two parts, having the subnet ID and the next one is the interface ID. So here the subnet ID contains the site prefix as well as the subnet ID. So these together makes the 64-bit long packet. And interface ID, it contains the part of MAC address of the interface or the device, and it will constitute the 64-bit together. So let's discuss about the its packet format. So here the first 3-bit is 001, that is the global unicast address prefix that we have discussed, and after that 45 bits represents the global routing prefix, and then the 16 bits are for the subnet ID and 64 bits are for the interface ID. So this is the constitution of the address of the global unicast address. How this global unicast addresses are made from this: it starts with 001, after that it has the 45 bits for global routing prefix, then subnet ID, and last one is the interface ID. Next, come to the next address, that is the unique local unicast address. So here the unique local address is also similar to the IPv4, but this is similar to the private addresses. So here it has the globally unique addresses. It means every device in the network have a unique address that is associated to it. So it is used in private networks such as within the corporate site. So to design a network within a company, so we can use these unique local addresses that will give a unique addresses to a particular device. So these addresses are not routable on the internet. It means if we want to access the another network or the internet, we can't access the network or internet using these unique local addresses. For that we have to we must have a public IP addresses to connect to the other network. So here it is configured through the DHCP v6. So these addresses are configured using the DHCP version 6. So after that it has a prefix of FD00 double colon and /8. So here the FD00 is the prefix and /8 is the prefix notation. So here the original IPv6 RFC defined a private address class which is known as the site local. So this is the format of the unique local unicast address. The first 8-bit represented as FD00, and next 40 bits will tell about the global ID. 16 bits will tell us about the subnet ID, and last 64 bits will give us the information about the interface ID. So this is the format of the unique local unicast address. So it will start with the FD00 and it will have 40 bits for global ID, 16 for subnet ID, and 64 for the interface ID. The next address is the IPv6 link local unicast address. So here the link local address has small scope. It means it is assigned in a very small organization or a very small network. Like it only applies within a network segment. So here the router will not forward packet to another network similar to as the unique local unicast address. These link local unicast addresses are not routable. It means it cannot be accessed outside the network. So it is configured automatically and manually. So it can be configured by using the DHCP version 6 or we can use the manual configuration to configure the link local addresses. After that, it is used for auto address configuration and neighbor discovery. So these link local address have a very significant role in finding the auto address configuration and the neighbor discovery. So it is have the prefix as FE80 double colon then slash 10. So here the FE80 tells about the prefix of the address and slash 10 is telling about the prefix notation. So let's see the link local unicast address format. So this is the format of the address. It will start with the first 10 bits are reserved for the prefix that FE80 and after that 38 bits are reserved for global ID and 16 bits is for the subnet ID and 64 bits are for the interface ID. So this is the format of link local unicast address. Next is the IPv6 embedded IPv4 unicast address. So here the IPv6 embedded IPv4 unicast address. Here the IPv6 transition mechanism include a technique for device and router to tunnel IPv6 packet dynamically under IPv4 routing infrastructure. It means if your device is present in a IPv4 routing infrastructure, like your device contain the IP addresses that are associated with IPv6. So if you are present in the IPv4 router configuration, for that you have to use the IPv6 embedded IPv4 unicast addresses. So there are two methods in this. The first one is IPv4 compatible IPv6 address. So here in this the IPv6 device are assigned with special IPv6 unicast address that carry an IPv4 address in low order 32 bit. It means the device, the IPv6 device which is present in the IPv4 network will have the IPv6, a special IPv6 unicast address in which it will embed a IPv4 address in lower order 32 bits. And the next method is IPv4 mapped IPv6 address. So here it is used to represent an IPv4 address within the IPv6 address space. So here what we are doing, we are representing the IPv4 addresses in between the IPv6 addresses. So it is mainly used internally within the implementation of application like APIs and the operating system. So these are the two methods in IPv6 embedded IPv4 unicast address. So let's see its format. So this is the format representing these two. So first one, here we are using 80 bits that are the continuous zeros. After that 16 bits are 0000 and 32 bits representing the IPv4 address. And in another method there are 80 bits with the continuous zeros and 16 bits with the FF and 32 bits are with the IPv4 address. So here the two addresses are pretty much the same. So the only difference is the 16 bit in middle. So when these are set to 0, the address is an IPv4 compatible IPv6 address, and if these bits are set to 1, then it is an IPv4 mapped IPv6 address. So these are the two formats for the IPv6 embedded IPv4 unicast address. The next one is the IPv6 special unicast addresses. So these special unicast addresses are like loopback unicast address and the unspecified unicast address. So here the loopback unicast address is used by a device to send an IPv6 packet to itself. So this is like a ping, to send a ping message to itself to check that the device is connected to the network or not. So these loopback unicast address are similar to that of IPv4 loopback addresses, and its format is it has continuous 0 with the last last 16 bit will have a 1 in last, and it prefix notation is as /128, or we can also represent it as :1. So the next one is the unspecified unicast address. So the unspecified unicast is represented by the continuous zeros, or we can also write it as we can write only the : to represent the unspecified unicast address. So here the unspecified unicast address, it is used in the source address field of the packet when an interface doesn't have an address and it is trying to acquire one dynamically. So here what happen if a device doesn't have any kind of address and it is trying to have an address from DHCP v6. So for that, what happen, it will specify it as unspecified unicast address. So it is represented by the : so it indicates the absence of address to a particular device. The next we are going to discuss about the IPv6 address scope. So as we have discussed about the number of unicast addresses, so what are the scope of these addresses? So the linked local addresses are assigned to a particular network or a very small network where there are a few devices having a unique addresses that will only communicate in within the network, but if they want to access the another network, they doesn't access. It means it doesn't routable to the outside network. So the linked local address having a very small scope, and they're also known as the local scope. And the site scope. So the site scopes are the corporate, like we are designing a network or a corporate company. So in that there are the multiple number of devices, and each devices have their own unique local address, so they can communicate in the network efficiently. So these addresses that are given to a devices in a site scope, that are representing the unique local address scope. So these devices, and similarly the devices cannot routable any of the data packet outside the network. For to route the packet outside the network, they must have the public IP addresses. So the unique local addresses have the larger scope as compared to linked local addresses. Coming to the next part, that is global unicast address, having the global scope because it is a, like, take an example of internet. So the global unicast addresses are addresses which have a number of devices, number of organization or corporate. It will constitute of the unique local address as well as the linked local addresses. It consists of site scope as well as the large number of local scope. So these together made the global scope, and it will make a network like a internet. So these are about the IPv6 address scope. So this is all about the unicast addresses. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the another kind of addresses that are associated in unicast addresses, IPv6. So in this class I will discuss about the 624 address, 6RD address, ISET TAP address, and the Teredo addresses. So let's discuss about the first, that is 624 address. So here the 624 address is defined to make IPv6 devices on network communication possible over an IPv4 infrastructure. So if we are deploying the IPv6 devices over a IPv4 infrastructure, then then we have to use the 624 address to make the communication easier between the IPv4 and IPv6 address devices. So here the INA has permanently assigned a 13-bit TLA identifier for 624 operation within the global unicast address range. So here it defines the 16-bit TLA identifier. So here this TLA identifier having a value of 0 into 0002. So this is the value that is associated with the TLA identifier, which is defined by the INA in the global unicast address range of 001. So here the interface for 624 with an IPv4 address of, like here I have using the IPv4 address 62.2.84.115, and I want to convert it into hexadecimal and then the 624 prefix. So when we convert it into the hexadecimal notation, it will become a 624 prefix. So here the 62.2.84.155 address will become 64 prefix like 2002 colon 3E02 colon 5473 double colon slash 48. So this is the representation of the IPv4 address into the 64 prefix. So this is the 64 address format. Here the first 3 bit is represented as FP001. So this will give the representation of first bit which will be start with the 001 and it is representing the fixed prefix. And after that 13 bit will represent the TLA identifier having the value of 0 into 002 and 32 bit will represent public IPv4 address. So here the address which we are going to use must be a public, and 16 bits will represent a SLA ID and 64 bits represent interface ID. So the prefix has a total length of 48 bit and the IPv4 address in the prefix must be a public IPv4 address and it must be represented in a hexadecimal notation. So this is the representation of 64 address for space. Next we are going to discuss about the 6RD address. So here the 6RD is also known as the IPv6 rapid deployment that is published in 2010. So here the 6RD addresses will not have a specific prefix, means it doesn't represented by a particular prefix as the other addresses are represented. So it also don't have a fixed boundary, it means its length is variable. So the prefix total length is 64 bit and it will constitute of the ISP prefix and the site IPv4 address, and these two are of the variable length. So here the main difference in the address is that 6RD doesn't use a special prefix like 624 and it doesn't have a fixed boundary like the 624 address have a boundary of /48. So this is the 6RD address format. Here the ISP prefix will have a variable length, then site IPv4 address also have a variable length, and after that subnet ID also represent a variable length, but together this constitute a prefix length of 64 bit and last 64 bits are represented by the interface ID. Next part is the ISATAP addressing. So here the ISATAP addresses stands for Intra-Site Automatic Tunnel Addressing Protocol. So here the automatic tunneling mechanism is specified in RFC 5214. So these automatic tunneling mechanism is specified by the IETF in RFCs. So it is designed for dual stack devices that are separated by an IPv4 structure. It means here there are 3 network, like in first network there are the IPv6 addresses. In between the network, in between there are network residing that will have most of the devices with the IPv4 addresses, and after that the last network will also have a IPv6 addresses. So if the first network want to communicate with the third network, then it must go through the IPv4 addresses that is lying in between, like if these IPv4 addresses are associated with the routers. So these routers must come in the route of these two network. So to pass this network of IPv4 addresses, there is a tunneling process. So these are designed for their dual stack nodes that will separate by a IPv4 structure. So the type identifier which will represent this address will have the value of 0 into FE, and type identifier specify an IPv6 address with an embedded IPv4 address. So here it treats the IPv4 network as one large link layer network, and it allows those dual stacks node or the devices to automatically tunnel between each other using any format of the IPv4 address. So for the short time they will use the IPv4 address format to pass that IPv4 network that is coming in between the communication of two IPv6 addresses network. So here there are the representation, like it will constitute of 64-bit, 32-bit. So let's discuss about these. So this is the format of this address ISATP. So this is the format, like 64-bit will represent the prefix, then 32 bits will have the two values. The first value is 00005EFE and the another value is the 02005EFE, and the last 32 bit will represent the IPv4 address. So here this first 64 bit will have the same format as the global unicast address. It means that this the first bit that is represented as prefix must have a format that same as the global unicast address. Next 32 bit, as INA owns the IEEE organizationally unique identifier, that is OUI, so it specifies the EUI 48 format for this 32 bit. So here it is represented as 00005E. So from these 32 bit, 16 bit of type identifier will represent two values. The first one is for the private IPv4 address, the second one for the public IPv4 address. Like these 16 bits will represent that it is from the public IPv4 address or the private IPv4 address. So here if 0000 is represented, then this address is associated with the private IPv4 address, and if it is represented as 0200, then it is associated with the public IPv4 address. After that, the 8 bits represent the type identifier, which indicates the IPv6 address within the embedded IPv4 address. So the value of type identifier is 0 into FE. And 32-bit, last 32-bit will represent embedded IPv4 address, and we have to represent it either in decimal notation or in the hexadecimal notation. So the example of the address I have given here is, like it is represented as 2001 colon DB8 colon 510 colon 200 colon 0 FEFE colon 192.168.0.1. So the first is representing the, that is in the green color, representing the IPv6 address, and the last, that is in the yellow color, this address is represented as IPv4 address. So this is the format of the ISATP address. Coming to the last, that is the Teredo address. So here the Teredo is designed to avail IPv6 connectivity to the devices that are present in one or the more the NAT networks. So here what happened, this is used to these Teredo addresses are used to give the IPv6 connectivity to the devices that are present in the NAT. So this is done by tunneling the IPv6 packet within the UDP. So here we will use the user datagram protocol, where we will tunnel the IPv6 packet with this protocol. So this method consists of Teredo client, server and relay. So here the Teredo relay are IPv6 router that are sitting between the Teredo service and the native IPv6 network. So these are the three devices that are present in the Teredo address format, that is Teredo client, servers and relay. After that, this address format is of first 32-bit, that is the prefix. Next 32-bit represent the server IPv4 address. Next 16-bit represent flags, and the another 16 bits will represent port, and the last 64 bits will represent the client IPv4 address. So here we are using 32 bits for the server IPv4 address and 64 bits for the client IPv4 address. So let's discuss about the first 32 bit will represent the prefix length, that will be start with the 2001 colon 0000 colon and /32. Last 30, and then the another 32 bit that represent the IPv4 address of Teredo server. Then 16 bits will represent the type of address and the NAT in use. So the which kind of address we are using, like unicast, global, unicast, anycast or multicast. And next 16 bit will represent the port field contain the map UDP port of Terudo service on the client. So this will represent the UDP port in 16 bits. And last 64 bits will represent the client IPv4 address field contains the map IPv4 address of the client. So this is all about the Terudo addresses format. So this is all about the other kind of addresses in IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the multicast addresses in IPv6. So in this class, I will discuss about the multicast addresses, the address format and the type of multicast address like solicited node multicast address and well-known multicast address. So starting with the first, that is the IPv6 multicast address. So what is a multicast addresses? The multicast addresses are the addresses that are given to the group of devices in a network. So in multicast communication, what happens? A single source will send a message to a multiple users or that are in defined group. So it means the message is sent to the multiple user and it is received by the multiple users simultaneously. So here an IPv6 multicast address define a group of devices known as multicast group. So a packet sent to a multicast group always has a unicast source address. It means a device which is sending a message or a data to a particular group, it will have a unicast source address. And as well, a multicast address can never be a source address. It means the multicast address, if a source or a sender use the multicast address, then it will able to send a message in a group. So it means if a sender if a device want to send something in a group, then it must have a unicast source address associated to it. So the prefix for IPv6 multicast address is as in hexadecimal it is represented as FF00, then double colon, then the /8, and in binary it is represented as 1111 and then 1111 and then the series of zeros 0000 00 and 00. Then IPv4 equivalent address, the IPv4 that is equivalent to this IPv6 multicast address is at 224.0.0.0/4. So this is the IPv4 address that is equivalent to the IPv6 multicast address. So the format of the IPv6 multicast address is as it is has 8 bit that is represented as series of 1, and in if we want to represent in hexadecimal it is represented as FF. Then is the 4 bit. So these 4 bit will represent the flags and next 4 bit will represent the scope field. So here the scope will define the range to which router can forward the multicast packet. So here it will define the router will send the message to in particular range or in which particular range. After that, this next 112 bits will represent the group ID. So here the group ID identifies the multicast group, either it is a permanent group or a transient group. So let's discuss about the first. We are going to discuss about the scope bits. So here the 4 bit that is represented as scope bit field, here if it is represented as 0, it means the scope of the multicast messages is reserved, and if it is represented by 1, then the node local, then it is a device local scope. If it is represented by 2, then it is a link local scope, and 3, 4 is represented as unassigned, and 5 is for the site local scope. 6, 7 is represented as unassigned. 8 is represented as organizational local scope. 9 A, B, C, D is represented as unassigned, and E is represented as global scope, and F is also represented as the reserved. So these are the values of the scope bit that will be used in a multicast 4-bit scope field. Next is the first 8 bits of the multicast address format. The first 8 bit is in binary format. It is represented as 11111111, and if we want to represent in hexadecimal, that it will be represented as FF. Next, then 4 bit that represent the flag. Here it is there are 4 different flags that is represented in that 4 bit. First one is 0, that is reserved. Then is R, that is rendezvous, and P is represented the network prefix, and T will represent the transient flag. So now we will discuss about the last flag, that is the T, transient flag. So here the T flag denotes the two type of multicast address, that is permanent address and non-permanent address. If it is if there is a bit 0, then it means it has a permanent address, and then if there is a bit 1, then it is a non-permanent address. So the permanent address is known as the predefined multicast address, and it is assigned by the INO. So here it includes well-known and the solicited multicast address in between, whereas non-permanent addresses are dynamically assigned multicast addresses by the DHCPv6, and it is assigned by the multicast applications. Next is the solicited node multicast addresses. So here its prefix will be FF02 colon 0 colon 0 colon 0, then colon 0 colon 1, and then colon FF00 double colon /104. So it is used in layer 3 to layer 2 address resolution, and it is automatically created using a special mapping of device unicast addresses. So these solicited non-multicast addresses are efficiently used as the broadcast addresses. As in this IPv6, we are not using the broadcast address, but this address, solicited non-multicast address, can be used as a broadcast address in IPv6. Next is the well-known multicast address. So here the multicast address have a prefix of FF00 double colon /12. So here the flag field is always set to 0, and these are predefined or reserved multicast addresses. So these addresses are equivalent to the IPv4 well-known multicast addresses that ranges from 224.0.0.0 to 239.255.255.255. So here the example of these well-known multicast addresses are like FF02 double colon 1 is represented as all IPv6 devices. FF02 double colon 2 is devices all IPv6 router. FF02 double colon 5 is given to the all OSPF PF v3 routers, and FF02 double colon A is given to the all EIGRP IPv6 routers. So these are the well-known multicast addresses. Next is the required addresses for hosts. If we are designing a network, and what are the addresses must be associated to the devices that is present in the network. So the first one, it must have a link local address for each interface. It means the first one, it must have a link local address. Then we have to assign any of the unicast or the anycast address. Unicast address for the source unicast address, and anycast address to finding as a nearest device. Loopback address must be there, multicast address to all nodes, then solicited non-multicast address for each of it assigned unicast and anycast addresses. Last one, multicast address of all other groups to which the host belong. So these are the addresses must be assigned to the device that we want to connect into the network. The next one is the required addresses for the router that we want to connect into the network. For that, the subnet router anycast address for the interface for which it is configured. So first of all, we have to assign a anycast address, that is subnet router anycast address. Then we have to assign anycast address with which the router have to be configured. Then multicast address to the all router and multicast address to other group to which the router belongs. So these are the addresses that are associated with the devices and the routers. So this is all about IPv6 multicast address. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the IPv6 interface ID. So as in previous lecture we have discussed about the different addresses format like the unicast address and the multicast address. So there is one field in between that format, that is the interface ID. So now we are going to discuss about this interface ID. So here these address interface IDs are of three types. So these types are like, first one is manual interface ID, second one is modified EUI64 interface ID, and the last one is the random ID. So let's discuss about these three one by one. First is manual IPv6 interface ID. So this is the, as its name suggested, so these IPv6 interface IDs are given manually. So this is used in servers, internet service and network infrastructure. So the example of these manual IPv6 interface IDs are like FD colon, GOFE colon and F11 double colon. It is FD colon 90FE colon F111 double colon then 100. So these are the interface IDs that are assigned manually. So the last 100 that is written in yellow color, that is the interface ID within this address, and in the second address the yellow color represents the interface ID, manual interface ID, that is FAAA colon B001 and double colon 1. The next interface ID is modified EU164 IPv6 interface ID. So this ID is assigned by auto addressing. It means we have in this particular interface ID we will modify something in the new form. So it is used in mobile devices, LAN host and IoT devices. The example of this modified EUI64 IPv6 interface ID is 2001 colon DB8 colon AA colon C10 colon and the next 12 CA colon EEAF colon FE11 and colon 31EF. So here the green color represents here that this is the previous field or the prefix of this of this address, and the rest one that is represented in yellow color represents the interface ID. So let's discuss about the further about this modified EU1E64 IPv6 interface ID is that a 64-bit interface ID is created by inserting the hex number, that is the hexadecimal number FFFE. So in between the 64-bit we will insert this number in middle of the MAC address of the network card by flipping the 7th binary bit to 1. So here what we are doing, we are inserting a hexadecimal number FFE in between the 64 bits, and then we are taking the MAC address of the network card and we are flipping the 7th bit to 1. If it is 0, then we are flipping it to the 1. So after this conversion, the interface ID is commonly called the modified extended unique identifier 64. So that's why it named as EUI64. So let us take an example here. If the MAC address of a network card or a device is 00 colon EE colon CC colon DD colon 55 colon and last is 22. So then interface ID will be 02 double E double C double F FE double D and 5522. So this will be the interface ID after converting this MAC address. So let's see in the steps how we will convert this MAC address to become a interface ID like this. So I'm taking the same example. So first of all, we will convert MAC addresses into the binary format. So I have taken the hexadecimal MAC address and now I am converting into the binary format. So here the binary format of this particular address is given below. After that, we have to flip the 7th bit from 0 to 1. So here I am flipping the 7th bit. Here you can see that in this binary format, this is the 4th, 5th, 6th and 7th. This one is the 7th bit. So here in next step I am converting it into the 1. So this is means we are flipping the 7th bit from 0 to 1. So now the hexadecimal MAC address will become 02 double E double C double D double 522. So here it is as 00 double E double C double D double 522. So it means there is a flip in between these two bits. Firstly it was 00, now it is 02. Then we have to insert the triple FE in the middle of the address. So to insert it, we have this hexadecimal code like 202 double E double C, and I am inserting a hexadecimal here FFFE. So in between I have inserted this hexadecimal code to the MAC address. So after inserting this, we will get the interface ID as, and we will separate this hexadecimal code with the colon. Like this is the interface ID 02 double E colon double C double F colon FE double D colon double F double 522. So this will be the interface ID after doing this conversion. So the step to make the modified interface ID, for that first of all we have to take the MAC address, then convert into the binary, then you have to flip the 7th bit from 0 to 1, and after that you have to insert the FFE hexadecimal code in between the MAC address, which will you get after flipping the 7th bit, and at last you will get the interface ID. So separate the hexadecimal code that you will get, and you will get interface ID at last. The last one is the random IPv6 interface ID. So here in random IPv6 interface ID, it is generated by auto configured address. So it is used in enabling and disabling security of LAN devices according to the usage. So here the random IPv6 interface IDs are auto configured, and they are basically used for the security purposes. So the example of this is like here I have taken a address 2001 colon db8 colon AA colon c10 colon 33c1 colon double c3f colon f711 colon 312f. So here the green part represents the prefix of this address, and the interface ID is represented in the yellow color. So these are the three different type of the IPv6 interface ID, that is the manual, second one is the modified, and third one is the random. So this is all about the interface ID in IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the ICMP version 6. So in this class we will discuss about the what is ICMP version 6 and its packet format. So starting with the first, let's start what is a IPv6. What is ICMP version 6? So ICMP version 6 stands for Internet Control Message Protocol version 6. So this is a new version of ICMP, as we are using this ICMP and the IPv4. So in IPv6 its name changed to the ICMP version 6, and we also add some of the functionality to this ICMP version 6. So here it offers a collective solution to different function. It means it is a single term that is used for a different functions, like it can perform ICMP, ARP, IGMP. So as earlier in IPv4 we will use ICMP only for the Internet Control Message Protocol, but and separately we use the ARP and IGMP. IGMP stands for Internet Group Membership Protocol version 3. So as these different terms are used for performing different functions in IPv4, but in IPv6 we have collectively used the ICMP version 6 to perform all of these functions. So it means it is a multi-purpose protocol. It performs plethora of activities including error reporting and packet processing, diagnostic activities, IPv6 multicast membership reporting, or performing neighbor discovery and the neighbor discovery processes. So these are the different function or the activities that can be performed by ICMP version 6 alone. So its value in the next header field is 51. So if in IPv version 6 packet format, if the next header field is 51, it means it is indicating that in extension header it includes the ICMP version 6 protocol. So next, this is the packet format of ICMP version 6. So here the 8 bits represents the ICMP version 6 type. Next 8 bit represent ICMP version 6 code, and the 16 bits represent the checksum data. And in IPv version 6, data consists of the 32 bits. So this will contain the data of the user. So let's discuss about it further. So first of all, the type field. So here in packet format, type field indicates the type of message and it is of 8-bit long. So here the high order bit, if high order bit is equals to 0, then it will ranges from 0 to 127 and it indicates an error message. And if the higher order bit is 1, then the value will be range from 128 to 255 and it will indicate an information message. So these are the two type of messages in ICMP version 6, that is error message and informational message. We will discuss about this later on. So after that, the next field is code. The next is type of messages that are contained in this type field. So the messages are like destination unreachable, packet too big, time exceeded, multicast listener messages, root salutation messages. So these are the different type of messages that is declared by the type field. After that, the total size of the ICMP version 6 packet should not exceed the minimum IPv6 MTU, that is maximum transmission unit. So here the value of maximum transmission unit is 1280 byte. So it means it can transmit a packet that is of this size. After that, the next field is code field. Here the code field will give the more detail about the message type. So whatever message type is declared in the type field, the code will give the more detail about that particular message type in 8 bits. After that, the next field is checksum field. So checksum field is particularly used for the detection of the error and it is of 16-bit long. And the last part is the data. So here it contains information according to the type of message and its length will be variable. Next part is the type of ICMP version 6. So these are the type of ICMP version, the error message and the informational message. So in error message, there is a destination unreachable, that is message type 1. So here if the field ICMP type field is equal to 1, it means it is indicating that the ICMP version 6 is indicating a destination unreachable message. If the message type is 2, then it will indicate packet too big, and message type 3 will indicate the time exceeded, and message type 4 will indicate the parameter problem. As well, in informational messages, there are two types, echo request and echo reply. So echo request, it is indicated by the message type 128 and echo reply is indicated by the message type 129. So these are the different type of ICMP version 6 messages. We will discuss about this later on in detail. So this is all about ICMP version 6. Thank you. Hello, welcome to the course of IPv version 6. So today we are going to discuss about the different type of messages in ICMP version 6. So the different type of messages in ICMP version 6 are error message and the informational message. So today we will discuss about these two both. So let's start with first, that is the ICMP version 6 error message, and the first one is the ICMP version 6 destination unreachable message. So here this is the packet format of destination unreachable packet. So this here the first field is ICMP version 6 type. So here in type field we have written 1. So this 1 indicates that this is a destination unreachable error message. After that, the ICMP code have the value ranges from 0 to 6, and then is a checksum field to detect the errors. Then is a unused field that is reserved for the future use, and last one is the ICMP version 6 data. So the total length of this field is 32 bits and the width of this field is 64 bits, except the ICMP version 6 data is not included in it. So let's discuss about this in detail. So after this, destination unreachable message is generated whenever the IP packet is not delivered at the destination. So that's why this destination unreachable error message indicates that the packet that you have sent to the particular destination, it is not reached. So this error message is indicated by the ICMP version 6 error messages. After this error message is sent back to the source host of the packet. It means this message is received by the source host who sends the message in the network. So the value of the type field is 1 and it's the code field value ranges from 0 to 6. So the first, if it code value is 0, then it is indicate that the destination is unreachable because no route to the destination is found. And if it is 1, then it indicates that the destination is unreachable because the communication with destination device is prohibited. And the next is, if it is value is 2, then destination unreachable indicates that the destination is beyond the scope of source address. Type value 3 indicate that destination is unreachable because of the address unreachable. And if the code field value is 4, then it indicates that destination is unreachable because of the port unreachable. The particular port to which we have sent the message is unreachable. Then is the further to 5 and 6 value of this code are further indicates that the destination is unreachable because of this particular problems. After that, the next part is data field will contain original data as the ICMP version 6 packet. So this data field is as data which will indicate the more information about the destination unreachable problem. So the next part is ICMP version 6 error message indicating the packet too big. The next error message is packet too big. So here the type field indicates the value 2, that will indicate that this is the error message of packet too big. And the code value here is 0, and there is a checksum field, MTU unit, that is maximum transmission unit, and ICMP version 6 data. The rest of the part is same, but there is a MTU in between this field, that is maximum transmission unit. So here the packet too big is generated whenever the error this error is generated whenever the packet size becomes greater than the maximum transmission unit value. So here the packet will be discarded by the network and error message is sent to the source host or the source generator of the packet. And the type field is equal to 2, code field is equal to 0, that is unused, and the value of MTU field is MTU size of the next hop limit. So these are the various features that are added to this error message packet too big. Next error message is the time exceeded. So here in this field the type field indicate the value 3, that means this is a time exceeded error message. Then the code will indicate the value of 0 and 1, then is checksum. Then after that the bits are unused, that is reserved for the future use, and then ICMP version 6 data. So here the time exceeded error indicate that the initial hop limit set by the sender is too low. It means the sender set the hop limit that is very low as compared to the number of hops coming in between the source and the destination. So here the hop limit is set in network to eliminate the routing loops. So here the value of type field is 3, value of code field is 0 and 1. Here the 0 will indicate that the hop limit was exceeded in the transit, and here if it is 1, then it will indicate the time is exceeded because for the fragment assembly time is exceeded. So these are the further explanation of the type field, and the value of unused field is 0. Next error message is the parameter problem. So here this error message have the type field equals to 4 and the code will be ranges from 0 to 2. And here there is a checksum field, and one more field is added here is this pointer. Then is unused field, that is set to 0, and ICMP version 6 data. So here this parameter problem error generated whenever IPv6 device is not able to complete the processing or identification of the type of the IPv6 packet. So this is the problem that will indicate that the IPv6 device is not able to process that what is the type of this IPv6 packet, that this is a what is the protocol of this IPv6 packet. So here the value of type field is 4 and value of code field is 0 to 2. So here if it is 0, it indicates that error header field encountered. There is error in the header field of the IPv6 packet. and if the code field is equal to 1, then it indicate that unrecognized next header type is encountered, and if it is 2, then it again that it unrecognized IPv6 option encountered. So there is a problem in the IPv6 packet that will result into the parameter problem, and the value of pointer will identify the offset where the error was detected. So it will give the particular position where the error is detected in the value of pointer. So this is all about the error messages. The next message is the ICMP version 6 if informational message. So this is the packet format of the informational message. So informational messages are of two type, echo request and the echo reply message. So here the ICMP version 6 type indicate two values, 128 and 129. So 128 indicate the echo request and 129 is for the echo reply message. And ICMP version code is set to 0, checksum field, and there is a new two fields added in here, that is identifier and the sequence number, and after that the ICMP version data. So identifiers are of 8-bit, whereas the sequence number is of 16 bits. So coming to the next part, yes, here the echo request and the echo reply message. So here it is used in TCP IP utility, that is the ping message. So these echo request and echo reply messages are used in ping, that is packet internet grouper. So ping determines the device that it is available on the network or ready to communicate. So the source device sends an echo request message to particular destination device, and then this destination device, whenever it receives the ping message, if it is available, it will send back the echo reply message. So that's why the type field will here is equal to 128 or 129 and code value is equal to 0. And here the identifiers and the sequence number are used to check synchronization between the request and the reply messages. So IPv6 authentication header is used to provide authentication to the echo messages here in the echo request and the echo reply messages. So this is all about the different type of ICMP version messages, that is error message and information message. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the neighbor discovery process. So here in ICMP version 6, it is also used for the neighbor discovery process. So let's discuss about this. In this class, we will discuss about what is a neighbor discovery, and after that we will discuss about its utilization and improvement in IPv4 protocols. So here the neighbor discovery. So neighbor discovery is specified in RFC 4861. So here this neighbor discovery is a combination of different processes like address resolution protocol, ICMP router discovery and redirect protocol, neighbor unreachable detection and the duplicate IP address detection. So here this neighbor discovery is doing a lot of work that in IPv4 is done by separated protocols. So here the address resolution protocol is to resolve the IPv4 address into the IPv6 addresses and simultaneously, and vice versa, sorry. After that is ICMP router discovery and redirect. This is the messages that we have discussed in next lectures. So after that is neighbor unreachable detection, that the neighbor to whom we are sending the message, that is in between the source and destination, is reachable or not unreachable. So this will detect the unreachable detection. After that, duplicate IP address detection, this will identify if there are two IP addresses that are similar to each other, so it will detect the duplicate IP address in the network. Next part is a function of NDP, that is the neighbor discovery protocol. So the first is neighbor discovery. So here this will discover or find the nearest neighbor in the source and destination route. Then it will discover the router. After that, stateless address auto configuration, it is used for this configuration stateless address, and then is address resolution. Another part is it is used for the neighbor unreachability detection and duplicate address detection. Last one is the redirection. So these are the various functions of neighbor discovery protocol. After that, the utilization of neighbor discovery. The first one is utilization is for the auto configuration. So it will do the stateless auto configuration of the IP addresses. Next one is the information regarding network prefix or route configuration is given by the neighbor discovery protocol. Next is to detect duplicate IP addresses. It is done by neighbor discovery, and to regulate the addresses of node at layer 2 on the same link, it is also done by the neighbor discovery. It will find neighboring routers to forward the packet. It will track the reachable and non-reachable neighboring nodes, and it will find changes in link layer addresses. So these are the utilization associated with the neighbor discovery. That is what is the improvement that we've done in IPv4 protocols to make it able to do the neighbor discovery protocol. So first of all, we have done the router discovery add to the base protocol, and then we have done the router advertisement contain link layer addresses for the router and prefix of a link. Then the resampling of a network is done by neighboring discovery. It is also provide the IP authentication and security in the network. Then is multiple prefix are assigned to one link and one particular link in the neighbor discovery process. Next part is neighbor unreachability detection. NUD detects the failed connectivity and not send message to the unreachable neighbor. Then the request above the hop limit value of 255 is not processed, and router advertise MTU on the link. And router advertisement also enable the stateless address auto configuration in the IPv6 protocol. So these are the various improvements that we have done in IPv4 protocol to make it efficient in IPv6. Next one is there is a 5 type of neighbor discovery protocol. The first one is the pair of neighbor solicitation and neighbor advertisement message. Next one is pair of router solicitations and the router advertisement message, and last one is the ICMP redirect message. So about this we will discuss about in next lecture. So this is all about neighbor discovery protocol. Thank you. Hello, welcome to the course of IPv6 version. So here today we are going to discuss about the neighbor discovery router messages. So as in previous lecture we have discussed about what is neighbor discovery, and in that we have discussed about the 5 different type of neighbor discovery messages. So in this we are going to discuss about the router messages. So here in this class we will discuss router solicitation message and the router advertisement message. So let's start with the first. We will discuss about these together, the routers, what is router solicitation and router advertisement messages are. So the first of all, the router advertisement messages. So these router advertisement messages is sent by routers at regular interval. It means at after some time the router that are present in the network will send the router advertisement messages. After that, coming to the next part, that these router solicitation messages. So the router solicitation messages are sent by devices to get the request of router advertisement. So here the devices request for the router advertisement by issuing a router solicitation messages. So after they will issue this message, this operation will trigger the router to immediately issue router advertisement irrespective of the regular interval. It means it will, as it will get the request, that is the router solicitation message, it will immediately give the router information in the router advertisement message. So this is the format of the router solicitation message, that will have a type field, code field, checksum field, reserved field, and the ICMP version 6 option. So in type field is equal to 133 and code field is equal to 0, and here reserved are these are the reserved bit that can be used in the future. So let's discuss about this in detail. So here the destination address, as this is a router solicitation message that is issued by the devices. So their destination address is the multicast address for all routers. So the router that are present in the network, it will add the multicast address of all the routers. So here it prefix will be as FF02:2, and after that the hop limit is set to 255. It means it will only go to the 255 routers in the network. Then ICMP type field value is 133, which is the router solicitation message type, and the code field indicate the unused, it indicate that is unused, and it is set to 0. Checksum field is of 2 byte that will detect the error in the message router message packet. And after that, there is a reserved field that is of 4 byte, and it is reserved for the future use, and the sender set them to 0 and the receiver ignore those fields. After that is a option field. So option field, if the address of the sending host is known, then an option contain the link clear address of the sending host. It means if the address that which of the particular device is sending this message, if the address of that sending message is known, then it will contain the link clear address of the sending device. And if the source address on the IP layer is unspecified, then this field is not used. So this is indicated as the all zeros. Next, this is the router advertisement message. Here it is of 32-bit long and the type is equal to 134, code is equal to 0, then is a checksum field, then hop limit, then there is a flag, there is a field that is M field, O, H and P reference. After that, there is a router lifetime bits field, reachable time, reserved and ICMP version 6 option. So let's discuss about this first. First we will discuss about the destination address. So as this is a router advertisement message, so it will contain the destination address as the multicast addresses of all the node, all the devices that are present in the network, and the prefix of for this is FF02:1, and this is the destination address when there is a periodic advertisement, that is the advertisement is sent after a fixed interval. And if the destination address is here if we get the solicited advertisement. So here the interface address that originate the solicitation message will be the address of the destination address. So here we will add the destination address of the source which will generate the solicitation message. The hop limit here set as 255 and ICMP type is 134, that indicate this is a router advertisement message, and code field is 0, that it is unused. Then there is a hop limit field that is used to configure all the nodes on a link. And then is M flag. M flag is of 1 bit and it is specify which configuration is to be used. So if the bit value is 0, then it state that all the devices use stateless or address auto configuration, and if the bit value is 1, then it will indicate devices can use stateful auto configuration. About these two configuration we will discuss in next lecture. Then is O flag. O flag shows the whether nodes on this link use DHCP version 6 for some additional information. So it means here whether these fields are using DHCP server for some other additional information, or they are only using for the IP address. So here if there is a bit field 0, then it indicates that device will use DHCP server for address related information. And if the bit field is set to 1, this will indicate that device use DHCP version 6 for non-address related information. So it is also gaining some other information related to the device. Next is the H flag. So here H flag is stand for home address flag, and here the bit value 1 indicate that it act as a home agent for the link, and if it is 0, then it indicates that this flag field is not used. Then is pre-reference flag, that is the optional extension that will define the route information, and it is of 2 bit, and after that the next 3 bits are set to 0 and they are reserved for the future use. Then there is a field named as route lifetime. This is of 16-bit long and it will have the maximum value of time, that is 18.2 hours. So if a bit value 1 is added here, that will indicate that router is used as default router, and if it is bit is 0, it will indicate that router is not used as a default router. We have configured the router with this route. Then is a reachable time. Reachable time is of 32-bit long field. It will indicate a time in millisecond, and when nodes are considered reachable, the NUD neighbor unreachable detection algorithm is used here. So here the bit value 0 indicate that the value is not declared, and if it is set, then it means it is using for the NUD algorithm. Last one is the retransmission time. Here the retransmission time field is of 32-bit long and it is used by ARP and UD mechanism. So it indicates the time in millisecond between retransmitted neighbor solicitation message. Here the bit field is equal to 0, that will indicate router is not configured with a retransmission timer. And here the last field is option field. Option field will contain 3 different information. So the first information is about the source link layer address. It will add the source link layer address of the sender, then MTU size, the maximum transmission unit size that is sent by the sender, then last it will indicate the prefix information. So this is about the router messages that we are using in the ICMP version, that we are using in neighbor discovery. So this is all about the router messages. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the neighbor discovery, neighbor messages. So as in previous lecture we have discussed about the router messages, now we are going to discuss about the next neighbor messages. So in this class I'm going to discuss about the 2 different messages, that is neighbor solicitation message and the neighbor advertisement message. So here the neighbor messages, first one we will discuss about these two both, neighbor solicitation and advertisement message. So first of all, neighbor solicitation. So this neighbor solicitation message is used by nodes to get the link layer address of the neighbor, and it is used to check whether a neighbor is still reachable via cache link layer address or not. It means here this neighbor solicitation message is basically used to get the link layer address of the neighbor, and after that it will check whether the neighbor that is the address of which neighbor is stored in the cache link layer, is it available or not. And here the destination address of neighbor solicitation message is added as multicast address, as we are sending this message in to a multiple users. Then is neighbor advertisement. Neighbor advertisement is used by devices to respond to a neighbor solicitation message. So here this neighbor advertisement message is sent by the nearest neighbor to whom we want to get the link layer address. So that particular neighbor will respond to this neighbor solicitation message by a neighbor advertisement message. And here the destination address is unicast address, that is the address of the source that will generate the neighbor solicitation message. So this is the format of neighbor solicitation message, having the type field equals to 135, code field equals to 0, then checksum, some bits are reserved for future use, target address to which particular neighbor we want to send this solicitation message, and ICMP version 6 option. So here 135 indicates in the type field that this is a neighbor solicitation message of 8-bit. Code is of code set to 0, that it is not used. Checksum is of 16-bit and it indicates that it is used for detecting the error. Reserve bit, these are reserved for future use. Target address. So here the target address is used in neighbor advertisement and redirect messages. So here the multicast message is not used here. Here we use the target address, that is 128-bit, that we have stored in the cache link layer address. After it, option field is of variable size and it contains the link layer source address. This is the neighbor advertisement message, having the type field equals to 136, code equals to 0, having the checksum field. Then there is a flag field, that is the additional field in this, and there is reserved field, target address, and the ICMP version option. So let's discuss about this in detail. First one, type field 136 value indicate that this is a neighbor advertisement message and it is of 8-bit. And here the code is equal to 0, that it means this is unused bit. Checksum here is used for detecting the error. Then there are a flag field. So in flag field, the first field is R flag, that is the router flag. So if this field is set to 1, that indicates the sender is a router. Then is the S flag, that is solicited flag. It is set while sending the response to a neighbor solicitation message. And O flag is the override flag. It will indicate the information of advertisement message that it override existing neighbor cache entries and update any cache link clear address. It means it is updating, it function is related to the cache link clear addresses. So it will update the cache link clear addresses according to the particular address that we are getting from these neighbor messages. So after remaining 29 bits are reserved for the future use and are set to 0. Target address, here we will add the address of the sender of the solicited message, that is 128 bit long, and option field will have a variable size containing the target link layer address. The last one, the neighbor advertisement message. Here if the source address is all 0, then destination addresses are all router multicast. If they are all router multicast, it means the message type of SLAAC. So if it is solicited not multicast, then it is a message type of DAT, that is the duplicate address detection. After that, if the source address is unicast, means source address we have added is unicast, and so destination address here will be solicited not multicast, and if it is solicited not multicast, then the message type will be resolved link layer address. Here we are resolving the link layer addresses. And if destination address is unicast, then what we are doing, we are detecting that the neighbor is unreachable or not, that we are running the NUD algorithm here. So this is all about the neighbor message in neighbor discovery process. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the neighbor discovery, redirect message, and the neighbor discovery security. So here, as in previous lecture, we have discussed about the router messages and the neighbor messages that are the part of the neighbor discovery protocol. So now we are going to discuss about the last message, that is redirect message. So in this class, we will discuss about this message and the neighbor discovery security process. So first of all, what is ICMP redirect message? So here this redirect message is particularly used by the router, and it sends information to the device over the link about the availability of the better path to particular destination. It means it sends the information about the path, that this is a better path to send the message as compared to the other. It means it will compare the different path and it will select out the better path to go to the destination. So here it also indicates that the distance of the destination device, that it is neighbor or it is neighbor on a same link or a node on a remote subnet. So here it is telling that the destination devices to whom we are sending the packets it is on the same link or it is available over to the remote subnet. So these are the two working of the redirect message. First of all, it will tell about the availability and of the better path, and next second one is it will tell about the it will tell about that the neighbor to whom and the destination device to whom we are sending the packet, is it on the same link or it is on the remote subnet. So this is a format of redirect message. So it consists of the type field, code field, checksum field. There are some reserved field bit in this reserved field, target address, destination address, and last one is the ICMP6 option. So here the type field has the value 137, which will indicate that it is a redirect message with 8-bit long, and here code is equal to 0. It indicates this field is unused and it is of 8-bit long. Checksum here is used to detect the error bit and it is of 16-bit long. Reserved field is indicating that these bits are reserved for the future use and it is set to the 0. Target address, here this target address address of next best hope is added here, and in destination address it is here we have added the address of the destination node to which we are sending the packet. And here if target address and destination address are same, it means destination is a neighbor node, not a remote node. So option feed here contains the target link layer source address and the redirect header. So better from IPv4 address where node sends the separate ARP request to determine the link layer address of the next hop. So here we in option field we are adding the target link layer source address as well as the redirect header. The next part is the neighbor discovery security. So here we are using a process name as SCND, that is Secure Neighbor Discovery. So this is a working group who defines the protocol that is used to secure the neighbor discovery messages. So it is, as we know, that neighbor discovery messages is used to cause various attacks in the network, so it must be protected. So protection of these neighbor discovery messages is mandatory. So it is used in a system where physical security of system is vulnerable to attack, and neighbor discovery security have a more concern over it. So three trust models are defined to secure the to provide the security to this neighbor discovery messages, such as first one is corporate intranet, second one is the public wireless access network, and third one is the pure ad hoc network. So we are providing the security to these particular network in neighbor discovery security. So here the component which define under the SCND working group are, first one is authorizing the router. So here what we are using, before using it as a default router, first of all we are authorizing it, that it is authorized by the it is authorized router or not. So here certification path, solicitation, advertisement message are used to discover the certification path to the trusted router in the network. So here these certification paths are used to find out the trusted routers or the certified router, authorized router in the network. Next is cryptographically generated process, that is CGA. So here this process detects the integrity of a sender of a neighbor discovery message by verifying its claim address. It means here we are checking the address of the sender, that it is sending the message from which we are receiving is that particular sender or not. So here the pair of public keys are shared between nodes before the communication. So these the data which is sent in between the sender and destination are encrypted properly. Second one, last one is the RSA signature. So here the RSA signature is used to protect our messages that are transferred related to the neighbor discovery as well as the router discovery. Next is the timestamps and the N1s option. So here these are used to prevent packet relay attack. So SEND doesn't cover the protection of address configured as static address or through IPv6 stateless address auto configuration. So here it only cover up the addresses that is configured by the SLA AAC, that is the stateful address auto configuration. So this is all about the neighbor redirect message as well as the neighbor discovery security. Thank you. Hello, welcome to the class of IPv6 course. So today we are going to discuss about the auto configurations and the path discovery processes. So in this class we will discuss about the stateful process of auto configuration, then the network renumbering, and after that the path MTU discovery. So starting with the first process, that is the auto configuration. So here IPv6 address have a ability to auto configure automatically in the network. So here, as in IPv4, the addresses are configured automatically or from the DHCP server. So it make the life of the auto configuration make the life of the network administrator easier, as especially when we have to allocate the address to a particular device. So here the benefit of auto configurations are like less workload on network administrator, as well as it make the easy configuration of the large addresses in IPv6. So these are the benefit of auto configuration. So here the IPv6 device can configure complete or part of address space for its automatically. So here it will configure some either the complete address, or it can configure a part of particular address automatically. So here the auto configuration methods are of two types. The first one is stateful auto configuration, and another one is stateless auto configuration. So here in stateful auto configuration, the IPv6 addresses are assigned with the help of DHCP server, that is dynamic host configuration protocol server. Whereas in stateless auto configuration, the devices and router have 64-bit prefix and 64 bits of interface ID. As we have discussed about the packet format of IPv6, we know that the 64-bit prefix are there, and after that the address has the 64-bit of interface ID. So here in stateless auto configuration, the interface ID addresses are derived with the help of EUI64 process. About this process we have discussed in earlier lecture. So here in the interface ID is automatically derived from the DSCP server in IPv6. So here the SLAAC use neighbor discovery protocol to configure addresses. So here the neighbor discovery protocol is used to configure the stateless auto configuration addresses. So here an IPv6 address are leased for a certain lifetime. So whenever the lifetime expires of the particular address, then the particular address will become invalid for use. So here we have to use a particular IP address that is not invalid in the network. The next we are going to discuss about the SLAAC, that is stateful auto configuration. So here in stateful auto configuration, it provides plug and play IP connectivity in two phases. The first one phase is link local address assignment, and the phase 2 is global address assignment. So here in link local address assignment, what happened here, we are providing the address to device that to provide a connectivity in a particular network or in a particular geographical area, whereas phase 2 global address assignment is a method in which we are providing an address to a device that it can communicate with the other devices or the external network efficiently. So first of all we will discuss about the first process, that is phase 1 link local address assignment. So here there are some steps to provide the link local address. So here it is used for providing local connectivity. So first step here is to that contain the generation of link local address. So here we have to generate the link local address. So here whenever a multicast capable IPv6 interface or a device is turned on in a network. So whenever we connect the IPv6 device in a network, and then a device generates a link local address for a interface, and this is done by giving interface ID to the link local prefix, that is FV80:10. So here after that the next step is execution of DAD algorithm. So here the DAD algorithm is duplicate address detection algorithm. So here for prior the assignment of the new link local address to its interface, the node must verify the address that address is unique or not. So this is done by sending a neighbor solicitation message to a new address, and if there is a reply, then the address is a duplicate, and if there is no reply from the message, then it means it is not a duplicate address. So if the address is duplicate, then the process will end there, and now the operator must take the concern about the address, and we can assign any unique code manually. After that the next process is link local address assignment, or the assignment of link local address. So here the next step here, if the address is unique, if that here when we run the DAD algorithm, and the result will come that the address is unique. So here if the address will unique, the node assign it to the interface. So the address will be assigned to the interface here. So this is how we can provide the link local address to a device so that it can communicate in a local area. After that the next step is phase 2, that is global address. So here this global address phase 2 process is used for providing global connectivity. So here there are steps. That first step is sending router advertisement message. So first of all we have to send a router advertisement message in a network. So here the node sends a router solicitation message to all on-link router to send it router advertisement. So when the router is enabled to provide stateless auto configuration support, the router advertisement will contain a subnet prefix that can used by the neighboring host. So here next step will contain the generating global address. So now the global address is generated after the router advertisement message is sent. So here as we get the prefix, subnet prefix of a network, then what we will do, once it receive a subnet prefix from a router, the next step is the host generate a global address by using the interface ID, and we will use that interface ID as compared to that subnet prefix. So next step will contain execution of DAD algorithm. Now the same steps are following. Now we will execute a DAD algorithm, that is the host will again perform a duplicate detection, like this address is present in a network before or not. So this time for a new global address we are performing this duplicate address detection algorithm. And the last step will assignment of global address. So we will assign the address to a particular device if that particular device is not a duplicate and it is a unique one. So we will assign that address to a host interface. So these are the two phases, that is phase 1, that is link local addresses, and this another phase will decide about the global address. Now we will discuss about the state of IPv6 addresses. So first of all we will discuss about the state of IPv6 address. There are 6 states, that is tentative address, preferred address, depreciated address, duplicate address, valid address, and the last one is invalid address. So here the first one is tentative address. That means it is an address that is not assigned yet in a network. It means we are not using that particular address. So it is a state prior to the assignment of the address to a particular device. So here what happen, we will verify the uniqueness of a particular address before assigning to a device. So here a node cannot communicate in the network using a tentative address, and the only message that can be processed with using a tentative address is that we can use a neighbor discovery message to run the auto configuration process. So these are the tentative addresses. The next one is the preferred address. So here the preferred address are the addresses that has been assigned to an interface and can be used without any restriction for a lifetime assignment. After that, the next is depreciated addresses. So here the use of this address is discouraged or banned, because a depreciated address might be one whose lifetime is about to expire, and we cannot use these particular addresses to be assigned to a new device in a network. So it can still be used to continue a communication that will disrupt the service if the address changes. So it is no longer used as a source address for a particular device. The next one is a duplicate address. So duplicate addresses are used to test the uniqueness of address by using a DAD algorithm, that is duplicate address destination. So here the next address is valid addresses. So here these valid addresses are used both for the preferred address and the depreciated addresses. So the valid addresses are those addresses that are assigned to a particular device and they are well communicating in a network. The next one is the invalid address. Invalid address are not assigned to an interface, and a valid addresses become invalid when its lifetime expires. So these are those devices at one time they are valid, and after some time when their lifetime expires they will become invalid addresses. So these are the 6 type of states that can be managed by the IPv6 address. So here before and after an IPv6 address is assigned, it goes through various states such as tentative address, duplicate address, and preferred addresses, and so on. Next we will discuss about the how to generate interface ID. So interface ID can be generated by using 2 methods. The first method is permanent IPv6 address and the next one is temporary IPv6 address. So in first one, the Here the global unicast address is assigned to interface either manually or by using a auto configuration method. So here it doesn't change as long as the interface is enabled and active. It means it will remain permanent. It will remain permanent in the network. The next one is the temporary IPv6 address. Here this globalcast unicast address is assigned to interface that use a random interface ID and that has a limited lifetime, and it changes regularly and configurable interval. So these are the addresses that can be chosen randomly interface ID but that have the limited lifetime, and it can be changed regularly or using a configurable interval. So these are two method of generating interface ID. First one is permanent and second one is temporary. Next we will discuss about the network renumbering. So here the renumbering a network means replacing an old prefix with a new prefix. So this is done to develop a new addressing concept in a network. So here the reason for replacing the prefix, the first one is like change of operator. So as the change of operator is called, it will usually implies a change of prefix. After that, the next is movement from IPv4 word to the IPv6 word. As we are doing the transition from IPv4 to IPv6, now we will have to change the prefix. After that, the next is concept of having multiple addresses to a node. So these are the reason of replacing the prefix. The next we will discuss about the path MTU discovery, that is path maximum transmission unit discovery. See here the path MTU discovery is a technique that will determine the MTU size on a network path between the two nodes. So it will find the MTU size, that is maximum transmission unit size, that we can use that we can send a packet of that MTU size on the network. So here the goal is to avoid the IP fragmentation or the IP packet splitting. Here the standardization of IPv4 path MTU discovery is defined in RFC 1191, and for IPv6 it is defined in RFC 1981. So here this also support the multicast destination addresses. So here the PMTUD was originally designed for router in IPv4, but in IPv6 router cannot fragment the packet anymore. So here we will use the IPv6 for the devices. So this work of fragmentation is done by the sender of a packet. So here we are using this path MTU discovery at the sender process. Now we will discuss how this path MTU discovery will work. The first of all, the device who is sending the packet over the network, what it will do, the device will believe that the path MTU is same as the MTU of the first hop link, and it will use that same size. First of all, it will send the packet to the next hop link in the network, and it will use the same path MTU as of itself. So here it will believe that the path MTU is same as that of the MTU of the first hop link. So here as it will send the packet of that size, after that ICMP version 6, that is packet too big message, is sent back to the sender. So here if the packet is too big for intermediate router along the path to deliver the packet to the next link, the router discard the packet. So here router will send the message, that is packet too big message, to the sender to indicate that the packet that you have sent have a larger MTU size. After that, the ICMP message includes the MTU size of the next hop link. So here what we will do, it use the MTU size of the next hop link, and it will use that much MTU size for a packet. So device use same MTU for sending further packet to the same destination, and when the packet received at the final destination, the path MTU discovery process will end. So this is the process in which path MTU discovery will work. So this is all about the auto configuration and path maximum transmission unit discovery. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the multicast listener discovery and multicast router discovery. So in this chapter we will discuss about the multicast listener discovery, after that its version 1 and version 2 and their packet format, and last one we will discuss about the multicast router discovery. So first of all, let's start with what is multicast listener discovery. So here the multicast listener discovery is used by IPv6 devices to discover multicast listener in a directly linked network. So here the IPv6 multicast group here is a group of receiver that want to receive a particular data from a source address. So here this group has no physical or geographical boundaries, and here the receiver can be located anywhere on the internet or in a private network. So here this multicast listener discovery process is used to find out the listener that are sitting in particular geographical area or in a private network. So here the protocol independent multicast, that is PIM, is the routing technique that is used for forwarding multicast messages in a network. So there are two versions of MLD. The first one is MLD version 1, that is based upon the IGMP version 2 for IPv4, and it is defined in RFC 2710. So here the IGMP is the Internet Group Management Protocol version 2. And after that the MLD version 2 is based upon the IGMP version 3 for IPv4, and it is defined in RFC 3810, and its additional information is and the enhanced information is added in the RFC 4606. So these are the two versions of MLD version 1 and MLD version 2. So let's discuss about the first version, that is MLD version 1. This is the packet format of this multicast listener discovery version 1. So here it is consists of 32-bit long packet, and here it consists of type, code, checksum, and the next field is maximum response delay. The next field is reserved, and the last field is multicast address. So let's discuss about this field one by one. So first field is type field. So here the type field have a value. It can contain a value of 130 that will indicate a multicast listener query, and if it will contain a value of 131, then it will indicate that it has a multicast listener report, and if it will have a value of 132, then it will indicate that is a multicast listener done message. So here if it is a 130, it means it contain a value of 130 that is used by a IPv6 router. So here it made the query that the multicast address is over a link. So there are two type of queries here. The one is journal query and the next one is address specific query. Here if it is a journal query, it will determine the multicast address that have listener on a link. It means the listener is present over on the link, and we have to find out its multicast address. Here the multicast address field, if it is set to journal query, then here the multicast address field is set to 0. After that, if 130 value will contain a address specific query, then it will find out whether there are member for a specific multicast address over a link or not. After that, here the multicast address field is set to multicast addresses of a device for which query is done. Here there are two queries, one is journal query and another one is address specific query. So here if it is a journal query, then it will find out a multicast address of a particular listener that is present over the link, and if it is a address specific query, then it will find out the address of a member of a specific multicast address over a link. And after that the next value is 131. So here if the value is set to 131, then it will use it this packet is used by a listener and it is used to register itself in a multicast group. It means it want to register itself in a multicast group. Next, second one is 132. Here the value is set to 132, and if it is set to 132, then it is used by or sent by a listener to deregister itself from a multicast group. So these two multicast listener report will request to add add the device in a multicast group, and if we will use multicast listener, then this message is used to delete itself from a multicast group. After that, the next field is code. So here the code field is set to 0 and it is ignored by the receiver, as it is sent by the sender, but it is ignored by the receiver. After that, the next is maximum response delay. So here it is used in query message only. So the maximum allowed delay is in millisecond, and the maximum allowed delay in which a node has to send a report if it has a listener. So this is a maximum response delay which is used by a listener, that it is used by a sender that will report. It is used by a device that has a report if it has a listener, and here in other messages this field is set to 0. The next field is multicast address field. Here this multicast address field is set to 0 if it contain a journal query, and it will set to multicast group address if it will contain a address specific query. So here in report or done message, this field contain either the multicast group to which a member listener is and or a group it is listening. So here these are the values of the multicast address field in MLD version 1. The next we will discuss about the message type that we are using in MLD version 1. So here if the message type is journal query, then what will happen? Here the destination address is added as a linked local scope of all nodes, and it is set to ff02:1. And if the message type is equal to multicast address specific query, then what happen? The multicast address that has been queried is added in the destination address. After that, if a message is a report message, then here the destination address will have a multicast address that have to be reported. And then done message, here if it has a done message type, then what will happen? The destination address will contain the link local address of all routers, and it will set to ff02:2. The next we will discuss about the MLD version 2. Here the MLD version 2 has a ability where node can do source filtering. So this is the difference between the MLD version 1 and version 2. It has the same similarities, but this is the one difference, that here it has ability where node can do a source filtering. So here what is source filtering? So here source filtering means either listening to packet with a particular multiple address from only specific source address, or from all source except from the specific source addresses. So here a list will contain a source addresses of a nodes that are present in multicast group, and here it will decide whether to send the packet to a particular devices that are added in the list, or not to send the message to that devices that are added in particular list. So here it will have a combination of SSM and ASM. So here SSM is source specific multicast and ASM is any source multicast. So there two filter modes are used that are supported by SSM are include and exclude. So here if it is include, it will include source address listed in source list are enabled to receive the packet. That means they are unable to receive the packet that have their name in source list. And in exclude process, here in this mode, all addresses except that listed in source list are unable to receive the packet. It means the devices that are having a address in the source list will not receive that particular packet. They are excluded from the services. Now this is a packet of MLD version 2. Here it is also of 32-bit, but it is a long packet which will have a field of type code, checksum, maximum response delay, and reserve and multicast. After that, the new fields are added over here, that is reserved S field, QVR field, QQIC field, and the next one is number of source addresses. And after that you have to add the source address, that the number of source address you're having, you have to add the address of that particular node source addresses. Starting with the first, the type field. So here the type field will have a value of 130 or 143. So here if it will have a value of 130, then it is a multicast listener query, and if it has a value of 143, then it will have a multicast listener report version 2, and it is defined in RFC 3810. Next bit is reserved, and this bit is reserved and set to 0. Next is S flag. So here the S flag is a suppress router side processing, and it is of 1 bit. And here when S is equal to 1 or it is set, then here it suppress the normal timer update at receiving multicast router side upon hearing a query. So here what will do, it will suppress the normal timer update of the router. After that, QVR field. Here QVR field is a courier robustness variable, and it is of 3 bit. Here when it is non-zero, it will contain the robustness variable value used by the courier. So this value affect timer and number of retries. So it includes queries in order to synchronize all the MLD version 2 router connected directly over to the same link. Then is QQIC, that is a courier query interval code. So this is of 8 bit, and it will specify the query interval that is used by the courier for the synchronization. And next is number of sources field. Here it is 16 bit, and it is represented as n, and it will specify how many source address are present in query. And if when it is set to 0, it means it has a journal query and multicast address specific query, and when it is set to 1, it means it has a multicast address and a source specific query. So in source addresses, it is of variable length, and it will contain source addresses of a node, and here the length is specified by the number of addresses specified in a n field. Next we will discuss about the type of query. So here there are 3 types of query: journal query, multicast address specific query, and the multicast address and source specific query. The first one is journal query. So here it is it is sent by the queries to get the information about the which multicast addresses have listener on a attached link. So it will get information about the multicast addresses that have a listener over a same link, and it will have a multicast address and a number of source field equal to 0. Then is multicast address specific query. Here it will give the information about if particular multicast address has a listener on a attached link or not. So here the multicast address field and multicast address of and the number of source field will have equal to 0, but here the multicast address field will have a multicast address of a node that will having that are over a same link. Last one is multicast address and source specifier query. Here it will give the information about if any of the source from this specified list of a multicast address has any listener over a attached link or not. And here a multicast address field will have a multicast address of a particular devices, and number of source field will contain the address of a source field, address of a source device. After that, the next part is multicast router discovery. So here multicast router discovery is used to search multicast router over a network, and it is defined in RFC 4286. So it doesn't have any specified routing protocol. So here we will use the 3 messages type, that is first one is multicast router advertisement, and next is multicast router solicitation, and last one is multicast router termination. So multicast router advertisement is used when a message is sent by router to advertise that IP multicast is forwarding as enabled. So here it is sent from a link local source address to all snooper multicast addresses. Then is multicast router solicitation. This message is sent by device in order to solicit advertisement message from multicast router, and it is sent to all router multicast addresses. Next is multicast router termination. This is sent by router to advertise that it stops IP multicast routing function on a interface, and here the multicast router discovery message are sent with an IPv6 hop limit equals to 1, and it will contain the router alert options. So this is all about multicast router discovery. So here we will discuss about the multicast listener discovery as well as multicast router discovery. So this is all about this concept. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the routing in IPv6. So in this chapter we will discuss about the MDT, that is multicast distribution tree, and we will discuss about the type of MDT, and then we will discuss about the PMI. So these are the protocols in routing. So let's start with the first, that is what is MDT. So here the MDT is a multicast distribution tree, and here this multicast capable router make this multicast distribution tree in the network, and here this tree is used to find the best path for multicast traffic from the source to the various listener or the receivers. So here the route at the source of the traffic is called shortest path tree, and the process of finding the upstream neighbor is called the reverse path forwarding, that is RPF. So here as the listener join and leaves the group, same way here the branches to the trees are added as well as deleted. So here like if the listener is joining the group or a multicast group, then here in MDT the branches are added to the tree, whereas as the listener are leaving this multicast group, then the branches will be deleted from this MDT tree. So here the unicast routing is concerned about the packet is going, whereas the multicast routing is concerned about from where the packet is coming. Next is here there are two type of multicast distribution tree. The first one is source tree and the second one is the shared tree. So here both the source tree as well as shared tree will are the loop free trees, and here the message are replicated or the loops are created whenever it reaches the tree branches. So let's discuss about this source tree and shared tree one by one. So first of all, what is source tree? So here the source trees are the simplest form of multicast distribution tree. So these it will have a roots as well as the branches, and its root act as a source and branches will form a spanning tree, and these branches will provide network to the various receiver or the listeners in a multicast group. So this tree will use the shortest path through the network, and it is also referred to as a shortest path tree. Next is shared tree. So here as the source tree have their roots at the source, but here the shared tree will use a single common root, that is it can be placed at any of the chosen point in the network, and it will act as a source to the it will act as a root to the tree. So this shared root is called as a rendezvous point in the IPv6. So this is about the source tree as well as the shared tree. So there is a difference between the source tree and the shared tree. So here the advantages of source tree is that it will create a optimal path between the source and the receiver. So this will result in minimum amount of network delay for forwarding the multicast traffic in the network. So as this is the advantage of source tree, it will be the disadvantage of shared tree. So here in shared tree, the path between the source and various receiver is not optimal under some of the conditions, and it will result into introducing a some of the delay in the packet delivery. The source tree disadvantage is that it will require a large memory consumption. So it will require large memory consumption due to the size of multicast routing table. As this is the disadvantage of source tree, it will be advantage of shared tree. So here it will require low memory requirement due to the minimum amount of state in each router. So these are the difference between source tree and shared tree. Next we will discuss about the PIM, that is protocol independent multicast. So here it is a process of building multicast distribution tree, and here the topology information is maintained in the tree information base, that is TIB. So here the type of multicast routing protocol are PIMSM, that is peer mode, PIM SSM, that is source specific multicast, and PIM BIDR, that is the bidirectional. So here let's discuss about the first, that is protocol independent multicast peer mode. So here it is used when multiple source devices transmit to a same multicast group. So here what happened is multiple source device, there are the multiple source devices in the network and they will transmit a same data to a same multicast group. And here is the example of this is like video conferencing. So here the next is PIM SSM, that is the protocol independent multicast source specific multicast. So here it is a subset of PIM-SM and it is used when single source will transmit a data to a multiple group. So here we are using a single source and it will transmit a data to a multiple group. And here the example is like the content delivery such as the video and the audios. And the last one is PIM bidirectional. So this is used when all member of the groups can be act as a source as well as a receiver or a listener. So here the devices that are present in a multicast group, they will act as a source and they can also act as a listener in the network. So this is all about routing in IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about routing. As in earlier lecture we have discussed about the various concepts of routing, and now we will discuss about like the routing tables, the entities that we will discuss in routing tables, the type of routes, static route, and there are static routing protocol and the dynamic routing protocol. So let's start with first, that is what is routing table. So here the routing table is a set of rules which will determine where to route the packet in the internet protocol network. So here the every packet which that are traveling in the network will contain the IP address of the source as well as the destination device. So whenever the router in the network receive this packet, it will match the address with the information that will it contain in its routing table, and as it will match the addresses that is contained in the packet, then it will find the best route to the transfer the packet in the network. So here the routing table can be maintained dynamically or manually, that is it can automatically attain the addresses from the packet and it will save it in the routing table, and in manually we will configure each of the IP address that is present in the network to the routing table of a router. So here the every router in a network will maintain the routing table. The next, the routing table entities. So here in IPv6 routing table entities are like IPv6 prefix and prefix length. It will contain the address, prefix and the prefix length. Next it will determine the next hop address. It means the packet will move to the intermediate devices in the network, then it will contain the address of the next hop address to which it will travel to the next. So here the next it will contain the next hop interface. So it will contain the information about the next hop interface, that is the local interface of router that is used to reach the next hop address. The next matrix. Matrix is a number that will indicate total distance to the destination. How many intermediate devices to be covered by the packet to reach to the destination. After that there is a timer that will give the amount of time since the information in routing table is last updated. So this will show the timer about the information in the routing table that is updated at which time. And last one, routing protocol use. So it will give the information about the which of the routing protocol we are using, like RIPNG, OSPF v3 or the BGP. So these are the routing this will give the routing protocol information. So next we will discuss how router will create a routing table. So here in a network, whenever a sender device sends the packet to the destination device, then this sender will add the IP address of a source as well as it will add the IP address of a destination. So then the packet will goes to the router, and here the router will examine the packet and it will find the IP address of the source as well as the destination, and it will match to the routing table of the router. So after matching this, after getting the perfect match, then it will determine find the perfect route, that is the cost effective route to forward the packet in the network. So in this way it will create the routing table and it will add the IP address of source and destination in its own routing table. And here if any of the new device will add in the network, then router will update the routing table according to the IP addresses. And here the router thus the router updates their information which is contained in the routing table to get the effective routing. So this is how the router can create the routing tables. Next is type of route. So here the type of route is like static route. So here the static routes are configured manually by the network administrator. It means the network administrator will add the IP addresses of each devices that are present in the network to give a static route information. So here the when any change in the network will occur, then a network administrator will manually update the static route according to the changes, and it is used for the simple and a small network, and it is a more secure route. So here the routing is a process of selecting the best path in a network. So this will static routes will provide a best path to route a packet in the network. Next is the type of static route. So there are 4 types of static route. First one is directly attached IPv6 static route. So here a directly attached IPv6 static route is created when specifying only outgoing interface. It means that is used to transmit or send the packet in the network. So here the interface type number parameter will specify the interface through which the destination network can be reached. And here the IPv6 prefix and prefix length parameter indicate the destination IP network and its prefix length. After that, the fully specified IPv6 static route. Here what happened, a fully specified static route is created when specifying the outgoing interface and whenever we have to define the next hop IP address. Next is floating IPv6 static route. Here the floating static route is usually configured when there are multiple paths to the destination network, and here a standby backup route is required to support IGP discovered route. So here it will only be added to the routing table if the IGP entry is deleted. So here it will create the backup route to which we can forward the packet if any of our main route is deleted. So here the next static route is default IPv6 static route. So here the IPv6 has a default static route similarly to the IPv4, and it is determined as 0. And here the IPv6 command use the :/0 to define this default static route, and this will use whenever we don't define the source and destination IP address, then the packet will be given to the default static route. Now the next part is static routing protocol. So here a static route is a special route that is configured by the network administrator manually. So here the static routing is a type of network routing technique that use the manual configuration and select the network route. And static routing is not a routing protocol. Instead, it is a routing technique, and it is used where the network parameters and environment are expected to remain constant, and it is used in a small network. Whereas the dynamic routing protocol is used to find the best path to forward the packet to the destination, it will automatically update the routing table according to the changes in the network. So here the common protocol that use the dynamic routing protocols are RIP-NG, OSPF-v3, ISIS and BGP, etc. So here the dynamic routing protocol can be divided into 2 parts, IGP and EGP. So IGP is the interior gateway protocol, whereas EGP is the exterior gateway protocol. Let's discuss about this. First one is IGP. So before discussing this, let's discuss about the autonomous system. So here the autonomous system is a collection of network that is managed by a single entity like INA or organization, and they follow different routing policies. So here in interior gateway protocol, here what happen, it is a set of routing protocol which are used within a one autonomous system, and here the example of these routing protocols are like RIP-NG, OSPF-3 and ISIS. So it mainly search and calculate routes within an autonomous system that is defined by a single entity. The next one is exterior gateway protocol. Here in exterior gateway protocol, it is used to connect different autonomous system, and the example of this routing protocol used in this EGP is BGP. So here it is used to connect the various autonomous system present in the network, and it will control communication between the different autonomous system with routing policies and routing filtering mechanism. So this is about IGP and EGP. So this is all about the routing in IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the routing protocol of IPv6. So here in this chapter we will discuss about the two protocols, that is RIPNG and OSPF v3. So let's start with first, that is RIPNG. So here the RIPNG is known as Routing Information Protocol Next Generation. So in IPv4 we will use this RIP only, but in IPv6 we will discuss about the Routing Information Protocol Next Generation. And this RIPNG is based on the distance vector algorithm, as IPv4 RIP is also based upon this distance vector algorithm. So here the concept for RIPNG is taken from RIP version 1 and RIP version 2. And it is specified in RFC 2080 in January 1997. So here RIPNG used the distance vector algorithm. So let's discuss about what is the distance vector algorithm. So here this mechanism will calculate the cost or metric of a route. It means it will count the number of hops that are the intermediate between the source and the destination. So here the RIPNG will support the maximum of 16 hop count. It means a packet that is transmitted from source to router will only cross the 16 intermediate devices that are present in between the source and destination. So the distance that is greater than 16 hop count will be considered as unreachable. And here the convergence time is a time that is taken by a device to know about all the routes in a network. So here the hop count is a count that will count the number of routers and that will present when packet will reach from source to the destination. And here the router will periodically distribute information about its route to its directly connected neighbors using RIPNG response messages. So this is the distance vector algorithm. It will calculate the cost of the route. So here the limitation of RIPNG, we are not using this RIPNG in IPv6 because it has some limitation. So the first limitation is the network area is limited, or there is a small network area. So the small network area is due to it can only transmit a packet to a 16 hop count. And next one is the presence of routing loop. So here the presence of routing loop in a network will cause a increase in convergence time, and it will make the system unstable. So here the next limitation is it doesn't measure other real-time parameter such as the link load, reliability, delay. So these are the parameters from which we can judge the network is good or not. So here in our IPNG it is not using such parameters to measure such parameter to create a better route. And the last limitation is that any change in the network structure will cause the instability in the network. So to overcome some of the limitation, the first one is split origin. So here it introduces a two part. That is, first one is split origin. Here a router will never advertise a route back over to its next hop interfaces. And in split origin with poison reverse, here a router always advertise a route back over its next hop interface with a metric of 16. So these are the two concepts that are used to overcome some of the limitation in RIPNG. But we are not using this RIPNG routing protocol in IPv6. The next we introduce the OSPF, that stands for Open Shortest Path First version 3, and it is specified in RFC 5340, whereas in IPv4 we are using the Open Shortest Path First version 2. So the fundamental OSPF mechanism and algorithm remain unchanged, but the packet and link state algorithm format are different in OSPF v3 and OSP v4. IPv2. So here this OSPF is introduced to eliminate the limitation of RIPNG. So the limitations such as it has a small network area, it will use a high conversions time, and it has a low metrics. So it will eliminate these drawbacks from the network. So OSPF consists of large routing table to accommodate large number of routers, and it will choose best path in a network on the basis of link state. So here the OSPF router will keep the information about the state of all network connection or link between the network. So as it is forwarding the packet or finding the best route by using the link state, so here the router will give the information about the network connection or the link. So in case of link failure, it also converges on a new loop-free routing structure within a seconds. So it will compute the shortest path tree for each route using the link state routing algorithm or a shortest path first algorithm. So here it calculates shortest path using a method based upon Dijkstra algorithm. So next is similarity between OSPv2 and OSPv3. So here these both a protocol will use a link state IGP routing protocol, and it will use a ABR and ASBR. That ABR is the area border router, whereas ASBR is a autonomous system boundary router. So after that it will use the SPF, that is shortest path first calculation with Dijkstra SPF algorithm, and both will use the metrics that are based upon the interface bandwidth, and both will have a 5 common protocol packet time: hello, data, database description, link state request, link state update, link state acknowledgement. These are the 5 protocol packets that are used in this both OSPv2 and OSPv3 routing protocol, and they will have a same LSA flooding and aging time. But the differences between the OSPv3 and OSPv2 are like they will use a different address family, because as OSPv2 is used in IPv4, so here the address space will have 32-bit, whereas in OSPv3 it is used in IPv6, so here the address space is of 128-bit long. And next it will introduce a new LSA format, because here as the address families are different, same way we have to change the LSA format as well as the packet format, and it will run per link rather than the per subnet, as OSPF is running over the per subnet basis, but in OSPF v3 it's running on per link basis. Next, it will support a multiple instances on a single link. Interface can have a multiple IPv6 addresses. So here in IPv6, a single interface will have a multiple IPv6 addresses. And after that, the OSPF3 is used a link local address, whereas in OSPF-v2 there is nothing like a link local addresses. And after that, in OSPF-v3 it will use a neighbor authentication by using a IP security, that is the field in a packet format of IPv6. So these are the similarity and differences between the OSPv2 and OSPv3. So this is all about routing protocol, in which we have discussed about RIPNG and the OSPv3. So this is all about the routing protocol in IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the routing protocol in IPv6. As in previous lecture, we have discussed about the two protocol, that is RIPNG and the OSPF-v3. So in this lecture we will discuss about the next protocol like ISIS, EIGRP and BGP. So let's start with first, that is ISIS. So here the ISIS stands for the intermediate system, and it is defined in RFC 5308. And here it is defined that the exchange of routing information between the intermediate system in the network. So here it is used to exchange information between the routers in a network, and it will share the OSI network layer protocol such as CLNP, that is connectionless network protocol, and CONP, that is connection oriented network protocol. So this will use these network layer protocols to exchange the information about the routers in the network. After that, integrated ISIS is an interior routing protocol that is based upon the link state updates. So integrated ISIS will provide the information about the variable length field that will contain type, length, value field. So these together will known as TLVs, and this will provide information about variable length field in all ISIS packet. The ISIS packet are like hello, LSP and SNP. So here the network layer protocol ID will tell about the network layer protocol, which is assigned by the ISO with a value of 142, that will have a value of 0x8E. And here the type of TLB for IPv6 ISIS are like IPv6 reachability TLB, and it will have a type field value as 226, and the next one is IPv6 interface address TLB, and here the type field will have a value of 232. Sorry, 232. After that, here in IPv6 reachability TLB, it will define the IPv6 prefix advertised within L1 LSP and L2 LSP, and here the following field will make up this TLB, that is prefix length, IPv6 prefix and matrix, and the control field. Whereas IPv6 interface address TLB will define the IPv6 addresses of one or more interfaces of the router, and it is advertised in hello packet, L1 LSP and L2 LSP. The next is EIGRP. So here it is stand for Enhanced Interior Gateway Protocol, and it runs in an autonomous system called the EIGRP domain. So here the main aim of the EIGRP is that it will eliminate the limitation of distance vector routing protocol without developing any another link state based protocol. So EIGRP is basically a hybrid protocol that will combine the best from both of the protocols, that is distance vector routing protocol and the link state routing protocol. So it will use a diffuse update algorithm to calculate the route. So it is interior routing protocol that is developed by a Cisco System Inc. So here the link state protocol, as it is not using the link state based protocol because it will have a more complexity and will use a database that will demand a higher CPU performance and more memory of the router. So it will use a batch from this distance vector routing protocol and the link state based protocols. So here the advantage of EIGRP is that it has a fast convergence time and it is a low free operation, and only the routers that are affected by the changes will be involved in the EIGRP. And EIGRP will support different network layer protocol, and here the semantic of different protocols are implemented using protocol dependent TLV, that is type length value field. And last one is BGP, that is Border Gateway Protocol, and is defined in RFC 4760. And here BGP is exterior routing protocol used to exchange information about the reachability of network between autonomous system. So this is used to communicate in between the two or different autonomous system. Each autonomous system receive a unique AS number, and it is assigned by the numbering authority such as INA, RIR. So these are the authority that will assign a number to the different AS in the network. So as there is no actual BGP for the IPv6, here the IPv6 will use BGP 4 to exchange information about the network layer protocol that will concern with the IPv4. So this is all about the routing protocol in IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about QoS, that is the quality of service of the IPv6 packet. So in this class we will discuss about what is QoS, and then the architecture of QoS and the flexibility in IPv6 header. So let's start with the first, that is what is QoS. So here the QoS, according to the basic IP model, all the packets in the network are treated similarly. That means all the packets are forwarded with the best effort according to first come first serve principle. So here the quality of service plays an important role. So here the quality of service will help in transmitting the packets as according to first come first serve principle. So to meet the demand of assessing real-time service efficiently, IPv6 provide a QoS feature. So QoS protocol have the task of providing different packet streams with priorities and metrics such as bandwidth, delay, inter-packet delay variation, that is also known as jitter, and the packet loss. So these are the parameters that are considered by the QoS protocol. So next we are going to discuss about the architecture of QoS. So QoS protocol consists of two main architecture, the integrated services and the differentiated services. So here both the services use the traffic policies and provide quality of service feature in both LAN and WAN network. LAN is local area network and WAN is a wide area network. So here the traffic policies are used to make transmission of data depending upon the various rules. So let's start with discussing first architecture, that is integrated services. So here these architectures offer a capability to allocate bandwidth to different flows. So here this architecture will define a bandwidth to different packets that are flowing in IPv6 network. So in this architecture, routers stores the information about the flows and it analyzes each packet separately. So based upon the model that provide assistance from end-to-end connectivity during the transmission of IP packet. So resource reservation protocol that is defined in RFC 2205, it is a part of InterServe architecture and it is a signaling protocol that is used to reserve bandwidth and other quality of service resources across on IP network. So this is about the integrated service architecture and it doesn't provide scalability to a network. The next we are going to discuss about the differentiated services. So here this architecture is designed to provide scalability and usability in large network and internet. So here there are some parts in this. First one is the DS domain. So here this DS domain is a neighboring group of routers having similar service policies that is implemented on all routers. So the boundary routers classify incoming data packets and label all the packets and use a peer hop behavior for all the packets. And after that the next part is DS region. So DS region is a set of neighboring DS domain and here it ensures the DS service for all domain spanning path. And last part is the packet classifiers. Here it checks the packet header information and it chooses the packet from the data network and it checks the packet header and verify according to the predefined rule of defining headers. So these are the part of the differentiated services: DS domain, DS region and the packet classifier. Next we will discuss about the type of packet classifier. So there are two type of packet classifier. The first one is the behavior aggregate classifier that is defined as BA and it classifies the packets based upon the DS field, that is differentiated service field. And after that multi-field classifier, it is defined as MF and it classifies the packet that based upon the different header fields, and the header fields are such as source address, destination address, the DS field, protocol numbers, source or the destination port information and the incoming over to the incoming interfaces. So these are the two type of packet classifier in the differentiated services. Next, we will discuss about the different fields in IPv6 header. So there are two different fields in IPv6 header. The first one is the traffic class field. So here the IPv6 offers flexibility as well as it supports different quality of service mechanism by adding functionality in IPv6 header. So first of all, here in traffic class field, it will consist of two fields such as DSCP and the ECN to provide the flexibility. So DSCP is the differentiated service code point. Here it defines the real-time data streaming application and it is used as this application will use the quality of service protocol, and the example of this is VoIP, that is voice over IP application. And next is the ECN. ECN is the explicit congestion notification. Here it carries information about the network congestion and it allows the end-to-end connection without packet dropping. The next part is the flow label field. Here the flow label field is used by the source to label the packet. So here basically a flow is defined as a sequence of packet from a sender to a specified unicast anycast or the multicast address labeled as a flow by a router. So here the value, its value ranges from 00001 to FFFFF. So here it is practically not used. We only use the traffic class field. So it is used for giving real-time application services and also help to detect spoofed packet, and this field requests the router to efficiently handle the packet. So these are the two different fields in IPv6 header. The first one is the traffic class field and another one is the flow label field. Most of the time we use the traffic class field and the flow label fields are not practically used. So this is all about quality of service in IPv6 packet. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the DHCP version 6. So in this class we will discuss about the what is DHCP v6, then the terms related to this dynamic host configuration protocol and the multicast addresses associated to it and the as well as ports. Then we will discuss about the DHCP version 6 header format and its authentication part. So let's start with first, that is what is DHCP version 6. So here DHCP version 6 stands for Dynamic Host Configuration Protocol version 6 and it is defined in RFC 3315. So here the operations of IP network greatly depends upon the DHCP version 6 for the addressing system, and for location services we will use the DNS server. So here we will discuss about the DHCP version 6. So IPv6 use the combination of SLAAC and DHCP version 6 for address configuration in network. So here the SLAAC is used for IPv6 address configuration using the neighbor discovery protocol. As we have discussed about this neighbor discovery protocol in earlier lectures. So here for the configuration of IPv6 address we will use the SLAAC protocol, and for here the DHCP version 6 server is used to provide additional information including DNS server IP address, DNS domain and other DHCP version 6 options. So it means IPv6 doesn't need DHCP to configure the device with address information. It uses SLAAC method to configure address that use neighbor discovery protocol. So for the dual stack network, it means the network that is running on IPv4 as well as IPv6. For that network, two separate DHCP servers are required. The first one is DHCP version 4 and the DHCP version 6. So here the host configuration address using DHCP server are known as stateful address configuration or the stateful DHCP version 6. It means if any device in the IPv6 network use DHCP server for the address configuration, then it is known as stateful address configuration or the stateful DHCP version 6. So next we will discuss about some of the terms that are related to DHCP version 6. So the terms that are related to DHCP version 6 is first one is DHCP client. See here the DHCP client is a device that sends requests to a DHCP server to get configuration information or the IPv6 address information. Whereas the next term is DHCP server. So here the DHCP server is a device that is configured to reply the client request. It means whatever the client is requesting, the server will reply according to that. After that, the next term is DHCP relay agent. So this relay agent, it is configured when no DHCP server is present on the client link. It means there is no DHCP server in between the link of the client or in the client network. Then the DHCP relay agent is configured that will send the message to the DHCP server outside the client link. There is DHCP unique identifier, that is DUID. Here each DHCP server as well as client will have their own DUID. So here the DUID of server is used by client to communicate with it, Same way, the DUID of the client is used by DHCP server to communicate with the clients. The next part is identity association, and it is also known as IE. So these identity association are the set of addresses that are assigned to the client, as well as identity association identifiers is the identity chosen by the client. So the clients are always identified by these identifiers known as IAID. Next part, the last part, is the transaction ID. So here the transaction ID is the value that is used to match requests and the replies that are coming from the client as well as the server. So this transaction ID will make a match between the request and replies. Next, we will discuss about the DHCP version 6 multicast addresses. So the multicast addresses that are associated with the DHCP version 6 server are: the first one is all DHCP relay agent and server. So here all DHCP agent like server and the relays are member of particular multicast group, and the address here we will use is #02:1:2, and here DHCP client use this address to reach DHCP agent on their link or the DHCP server on their link, and DHCP doesn't require any of the link local address of the agent. It means the client who want to communicate with the server will not require any of the link local address of the server. The next part is all DHCP server address. So here all DHCP server present within sites are member of multicast group, and the address associated to it are FF05:1:3. So here DHCP relay agent or the server use this site scope address to reach all DHCP server within a site. It means the relay agent that are present in between the client link use this site scope address to reach or to search all the DHCP server that are within a particular network. So these are the two multicast address associated with DHCP server. Next, we will discuss about the UDP ports that are associated with DHCP version 6 server. So UDP are the user datagram protocol. So UDP port 546 is a client port, and here the client listen the DHCP message on this port, and the DHCP servers and the relay agent use this port as a destination port to reach to the client. Next is UDP port 547. This is a server agent port. DHCP server and relay listen DHCP messages or the request messages on this port, and the DHCP client use this port as a destination port to reach the DHCP server and the relay. It means it is a source address for the DHCP server and the relay agent, whereas it is a destination address for the DHCP client. The next, this is a header format of the DHCP version 6 server. The message type, transaction ID and the option are the part of this header. Let's discuss about this. First one is there is a client server message header format. So the first part is message type. So message type, it is of 1 byte and it indicates the type of message. The type of message may be a solicit, advertise, rebind, reply, renew message, the request message, confirmation message, release message and the decline message, etc. After that, the transaction ID, it is of 3 byte long and is used to troubleshoot server, and for each request client generate a new transaction ID. After that, the next part is for the option. Option will have a variable length and it will provide the configuration information and the parameters. So it will have its own type in between. The first one is option code. It is of 2 byte and it will tell the type of option. And so the type code will have a message like reply message, option request message, the server identifier or the client identifier, and the preference or the authentication part. So these are the type of options that are included in option code. Next is option length. This is of 2 byte long and it will indicate the length of the option. Next, option data. This is of variable length and it contains the information that is used for configuration. So these are the part of the header of DHCP version 6 protocol. Next, we will discuss about the authentication header format. So here the authentication header format will have first part of option code, that is of 2 byte, and it is set to value 11. And then is the option length will have a value of 2 byte, and it will tell about the length of the option. So here the DHCP version authentication header format is used to reliably identify the source of a DHCP message and to confirm that the content of the DHCP message have not been changed. So particularly this is for the authentication of the DHCP message in the network. So option code here, it contains information to authenticate the identity as well as the content of DHCP messages. Then coming to the protocol part, it is of 1 byte long and it contains two kind of protocols, and the two kind of protocols are delay authentication process and the reconfigure key authentication process. If its value is 2, then it will have the protocol as delay authentication process, and if it has a value of 3, then it will contain the configure key authentication protocol. The next part is algorithm. Algorithm will be of 1 byte, and it will indicate the type of algorithm used for the DHCP version 6 packet transmission. After that, RDM is the replay detection method. It is of 1 byte, and it will tell about the type of method used for giving the reply of the requested message. Then is replay detection. It is of 8 byte long, and it will give the replay detection information. And next, the last part is authentication information. It is of variable length, and it will give the detail about the authentication process used in the DHCP version 6 packets. So this is all about the DHCP version 6 in IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the DNS server. So in this class we will discuss about what is DNS, then the term associated with the DNS server, and then the working of the DNS, and then happy eyeballing and DNS security extension. So let's first start with very first, that is what is DNS. So here the DNS is a name resolution protocol, and it is known as domain name system server. So it is a powerful, extensible and flexible system that is used for resolving name over an entire internet. It means it is used to resolve the name of the URL to a particular IP address or the resolution of the IP address to a particular URL. So here the DNS uses TCP port 53 and UDP port 53 for the resolution. This technology makes easier for the people to remember the words rather than the number, as it is very difficult to remember the IP address for each website. So these DNS servers make it easier for the people to remember only the URL of a particular website. For example, as we want to open a web page for a Google, we will type www.google.com instead of typing its IP address as http://2001:4860:4860:8844. So this is the IPv6 address associated with the Google website. So as we want to open this website, we only type the URL. We will not type the IP address of this, as IP address are not easy to remember for the people. So here the need of DNS is more in the IPv6 because it is very difficult to remember such a long address for a different website. So let's start with first that what is a DNS server. So DNS server is a collection of computers that want to join domain name system. So they work as a team and collectively known as DNS root server. So the internet name of this computer team is dot. We will use the dot to represent the DNS server in the internet system. So the DNS servers are organized in a hierarchical form, which include the top level domain names such as .com. For the organization we will use .org, for the network we will use the .net, and for the educational institute we will use the .edu, and for the government website we will use the gov, etc. The DNS root servers are the top level domain servers, and it include a complete database of internet domain names and their corresponding IP addresses. So the low level DNS servers are owned by the businesses and the ISP, that is the Internet Service Protocol. So this is the hierarchy form and the DNS server system. After that, the next part is the terms that are associated with the DNS. So the very first term is the domain namespace. So the naming system on which DNS is based is a hierarchical and imaginary tree structure called the domain namespace. So it includes all the possible names that could be used within a single system, and each node in the DNS tree represent a DNS name. So this is the form of a naming system in DNS, that is domain name space. So here a diagram shows that there is a, first of all, there is a root that is represented as a dot. After that, top level domain names are like .com, education, org, and the others. And the second level domain names are the name of the website, like Telcoma Trainings, that is the name of the website, Stanford, and physics. So these are the particular names that represent the second level domain name. After that, the subdomain name is the www, that is World Wide Web. So whenever we type a particular URL like www.telcomatraining.com, then it represents a complete address of a particular website, and whenever we type this, the DNS server resolves this particular URL to its IP address. So there are the top level domain names, second level domain names, and the subdomain names in a domain namespace hierarchy. Then is the name server. So here the name servers include the DNS name server, zones, and record. So first of all, what is a DNS name server? So it is a computer that has DNS software installed on it, and it is specially designed for managing the different domain names. After that, the zone. Zone is a container which holds the records of a single domain. Here a simple network has a DNS server for the entire network, and a single domain name can use more than one DNS server. For example, like a google.com is a busy domain, so it needs multiple DNS server to support all the incoming DNS queries from the user. For that, we have to represent a multiple DNS server for a particular domain name. So the next part is record. Record is a line in data that contained by the zone which maps an FQDN, that is fully qualified domain name, to an IP address. Means whenever we write the www.telcomatraining.com, it will represent a complete URL, that is FQDN, and then it is resolved to a particular IP address in a network. So this is the meaning of DNS name server, zone, and the record. After that, the next part is the IPv6 define the two type of record types. The first one is Squad A, that is represented as Squad A type record, and it is represented and defined in the RFC 3596. And the second record type is A6 type record, and it is defined in RFC 2874. So the A6 type record is designed to make renumbering of network and prefix changes easier for the network administrator. And the other DNS records are also there, like NS records and PTR records. They remain unchanged as they are also present in the IPv4. So only these two are supporting the changes for IPv6 network, that is Squad A and A6 type record. Next is the name resolution. So the name resolution means successfully mapping a DNS domain or host name to an IP address. So there are many ways to resolve the name in DNS, like by broadcasting. So the particular host that want to know its IP address or the host name, then it can broadcast its particular host name to know the IP address, and if it knows the IP address, then it can broadcast the host name in a, but this part is only take place in a small network. The next part is the by locally consulting the locally stored host text file. It means we can consult a locally stored at a database that can contain the text file that contain the information about the IP address and the host name of all the all the computers that are present in the network. After that, by contacting a DNS server. So last, this is a main role. This play a main role in DNS, that we can contact a DNS servers to resolve the name of the host name to a IP address. Next part is the how DNS server work, or the working of DNS server. So here the DNS act as a central part of internet, and it provide a way to match website names or the computer names to their IP addresses. So first of all, a user type the name of website in search engine, and which generate a query and is sent over the internet. So this is the first part. Whenever a user type a name of the website, it will generate a query. So let's suppose the user query first go to the recursive server that is operated by an ISP, and it is present in this client link or a user network. So the recursive resolver know where to send the query in the network. After that, then recursive resolver talk with the root DNS server about the IP address of the website. So it will talk to this root DNS server about the IP address of the network, and then root DNS server search for its particular top level domain TLD by analyzing the domain name of the website. So it will analyze the domain name and find out the particular top level server. So when it finds the top level server, the query is sent to the particular TLD server, where TLD server stores the address information for the second level domain within the TLD. So the second domain level is the name of the particular website. So this is the top level. It will decide for the top level, and then it is decide for the second level domain. So whenever it gets the information about the second level domain, then the TLD server gives the IP address of a particular DNS, which knows about the IP address of a website to a recursive resolver. So here the IP, it knows the IP address of a particular DNS server that knows the complete information about the URL that we have typed in, that the user typed in the computer. So it will send the IP address of particular DNS, and then root DNS server will again send the IP address of the particular DNS server to the ISP, that is the recursive resolver. So after that, as the recursive resolvers know the IP address, then recursive resolvers send the query to the DNS, as DNS knows about the IP address of full domain, and it tells the IP address of the website. So as now ISP know about the IP address of a website, or know the IP address of a DNS server that contain the information about the particular URL, then it will send the query to that DNS server, and then it will extract the website IP address from that DNS server. So here the recursive resolver send IP address of a website to the user, and thus the website appears. Now user can browse the website and retrieve the content using the IP address. So this is the working of a DNS server in a network. After that, the next part is DNS dual stack query. So in the case of dual stack network, whenever a host query a DNS server for service name by entering a URL in a browser. So a dual stack network is a network where we have the IPv4 as well as IPv6 addresses present. So the client sends the two DNS requests, a record and query a record. So the DNS can use either of them or both to answer the query according to the DNS configuration. And when client receives two addresses, then address is chosen according to the default selection rule. So this is depend upon the DNS server and the client to choose which of the address by in a dual stack network. Next is DNS Happy Eyeball. So this is a method which is used to improve the client experience in a dual stack network, and it is defined in RFC 6555, and its operation is like when a client gets two addresses for a given service such as IPv4 and IPv6 address. By default, it will connect to the IPv6 address by initiating a TCP handshake. First of all, it will choose the IPv6 address to connect. If no reply is occurred of the request, the client wait for long time, and when time outs, then the client use IPv4 address. So the reply node comes due to the slow and broken IPv6 path. Then with the implementation of Happy Eyeball technology, the client can try both the protocols and then can use the faster one for the communication. The next part is DNS security extensions. The DNS security extension, that is DNS SEC, is an authentication and authorization protocol to provide security to DNS server. So DNS SEC is a suite of Internet Engineering Task Force specification, and here the securities are added to protect DNS from unauthorized user. So DNS SEC is implemented through extension mechanism for DNS, that is eDNS. So this is all about the DNS server in detail, and thank you. Hello, welcome to the class of IPv6. So today we are going to discuss about the IP security. So in this class we will discuss about the what is IP security, and in that we will discuss about the security traits. Then non-reportization, IP security, security associations, and the key management. So let's first start with what is security traits. So there are two types of traits that are defined by the security standards, that is CIA and EEE. So here the CIA stands for confidentiality, integrity, and availability. So here the confidentiality should stored or transmit information that cannot be read or altered by any unauthorized party. Whereas integrity, it means any changes of transmitted or stored information can be detected. After that, the availability is the information in question is readily accessible to unauthorized user at all time. It means if it is accessible or not at all time. After that, the next part is the triple A, that is authentication, authorization, and accounting. So authentications here stands at the act of clarifying a claim identity. That means the person like adding a username password. So it is a way of authenticating a user like adding a ATM card pin. So these are the examples in the authentication process. After that, authorization ensures that the authenticated user or a group has the proper right to access the information they are attempting to access. So these include the access control list, and these access control lists contain the name of the authorized user. After that, accounting is the act of collecting information on resource usage, like the logs of HTTP server. So these are the two traits of security standard in IP security. And the next part is non-reportization is not included in CIA and in AAA trait. So here the non-reportization means it specified actions such as sending, receiving detail of information, and that cannot be detained by any of the parties involved. So this is non-reportization. It means we are sending and receiving information that cannot be denied by any of the parties involved. So there are two security elements in this: the encryption and the secure checksum and hash. So these two security elements provide the confidentiality and the integrity. So here the encryption as the combination of both result into a complex service such as authenticity and the non-reportization process. So encryption here provides the confidentiality, and it is further divided into two parts, that is secret key cryptography and the public key cryptography. So the secret key cryptography is the symmetric key encryption. Here, the sender and receivers agree on a shared secret keys that is used to encrypt and decrypt the information exchange. An example of secret key cryptography are like advanced encryption standard, the data encryption standard, the international data encryption standards, and the Ronald Rivest 4. So these are the various algorithms that we can use in a secret key cryptography. The next part is the public key cryptography. So here the two type of keys are used, the public key and the private key. The public keys are accessible to anyone whom we are not trusting or whom we are trusting, and private keys are only given to a trusted user. So here the asymmetric cryptography has two primary use cases like authentication and confidentiality. Using asymmetric cryptography, message can be signed with a private key, and then anyone with the public key is able to verify that the message was created by someone possessing the corresponding private key. So here the example of this like L-Gamma algorithm and the ECC, that is elliptic curve cryptography. So these are the example of public key cryptography. The next part is the secure checksum and hash. So it provides the integrity. So the combination of both will lead to the complex security system. And here the IP security standard use a combination of algorithm choices based upon the symmetric and asymmetric cryptography as well as on the one-way hash function. Next is IP security. So IP security is specified in RFC 4301 and it defines the security architecture for both IPv6 and IPv4 version. So it creates a boundary between the protected and unprotected area. And the security requirement in IP security is defined by a security policy database, that is SPD. So here the IP security defines like the description of security requirements and mechanisms at the network layer, and how to use cryptographic algorithm for encryption and authentication. Then the security policies and security associated with communication devices. Then protocol for encryption like encapsulating security payload, and protocol for authentication like the authentication header. Then the last part is the key management. So these are the part of IP security. So next we will discuss about the security association, that is SC. So SCs are a set of agreement between the communication devices. So there are three elements of agreement between the communication devices like the keys, inscription or authentication, and the additional parameter for algorithm. So here the SCs are unidirectional, that means each security service requires the separate SC. This means that two communication devices who want to encrypt and authenticate a two-way communication need four assays, one pair for encryption and the other two pair for the authentication. So then these assays have the two mode of transport. The first mode is transport mode. So assay is made between two communication devices, and encryption or authentication for payload of all IP packets is done in this transport mode, and the IP header is not encrypted in particular mode. After that, internal mode. This is a method that a assay mode between two security gateways are consistent, like the two security gateways are like a firewall. So here the whole packet includes the original IP address is encrypted or authenticated by encapsulating into a new header. This means this is a foundation of VPN, that is the virtual private network. So these are the two modes in between the assay, that is transport mode and the tunnel mode. The next part is the key management. So IP security use the cryptographic key, and these support the manual and automated distribution of the key. So IKE, that is Internet Key Exchange, specifies a protocol that allow for the exchange and negotiation of parameters for assay. So the first one is IKE version 1, that is Internet Key Exchange version 1, and Internet Key Exchange version 2. So as IKEV version 1 is not approved, also that why it replaced by the AKE version 2, but now it is widely used today. So the first one is IKE version 1, Internet Key Exchange version 1. It is specified in RFC 2401 and it is updated in RFC 4109. So this includes the three protocols like ISA-KMP, that is Internet Security Association and Key Management Protocol, which specify the framework for the management of SC and key exchange. So it doesn't specify processing detail, but it supports different key exchange mechanisms. After that, the Oakley key determination protocol, it is used in the exchange of keys and it is specified in RFC 2412. So here the extension of algorithm is defined by the Diffie-Hellman and it is only used the subset of the function of this protocol. After that, the next part is SKEMA, that is the versatile secure key exchange mechanism for the internet. So here it is a fast key exchange technique. It defined in IEEE proceeding of 1996 synonyms on network and distributed system. So here here it only use the subset of function of this protocol. So here IKE version 1 use the UDP on port 500 and 4500. This is about the Internet Key Exchange version 1. The next is version 2, Internet Key Exchange. It is specified in RFC 5996 and it brings the enhancement in the IP security while using with NAT for authentication and for remote address acquisition. So here it the simplified use of IKE is by replacing 8 different initial exchange with single 4 message exchange. So it reduces error due to reliable protocol as all messages are sequenced and acknowledged. So this is the information about the Internet Key Exchange version 2. So this is all about the IP security in IPv6. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the transition processes in IPv6. So here in this class we will discuss about the different transition process like the dual stack, tunneling and the header translation. So let's first start with discussing about the transition from IPv6 by IP addresses. So here due to huge number of devices on internet, the transition from IPv4 to IPv6 cannot be happen suddenly. So here to make communication possible between every devices in the network, we need transition from IPv4 to IPv6 address. So the type of transition are dual stack, tunneling and header translation. So let's discuss about this one by one. The first one is the dual stack. So here in dual stack, a router or a host is equipped with both IPv4 and IPv6 protocol version. It means it knows the rule of IPv4 as well as IPv6 addresses. So here the modes of operation exist in dual stack. The first one is IPv4 only node. So here when IPv4 stack is enabled and IPv6 stack is disabled, the node behaves like as IPv4 only node. As and in another IPv6 only mode, here when IPv6 stack is enabled and IPv4 stack is disabled, the node behaves like a IPv6 only node. And in IPv4 and IPv6 node, here when both the IPv4 and IPv6 stack is enabled, the node can use both protocols. So it means the dual stack network is an infrastructure where IPv4 and IPv6 packet forwarding is enabled on a router. So here the advantages and disadvantages exist in dual stack. The advantages are like smooth shift of traffic from IPv4 to IPv6 and no tunnelings or translation is required of the packet, and then best performance, stability and efficiency of a network is in the dual stack transition. And disadvantage of this is that it takes more memory and CPU power as it is to remember the rules of IPv4 as well the IPv6 addresses, and it is a complicated troubleshooting process as if here we need to troubleshoot the router that knows the IPv4 and IPv6 address, that is a complex process. So but the advantages are more than the disadvantages, so we are using the dual stack transition in our network. So here this diagram shows the dual transition. So here a host from IPv4 as well as IPv6 can access the server with the help of dual stack router. So this router is acting as a dual stack router that it knows the rules of IPv4 and IPv6 addresses. So any of the hosts that want to access the server, it can use this dual stack router to communicate with the server as well as IPv4 user. So the dual stack router can communicate with both the network, and router can send and receive data belonging to both protocols simultaneously. The next process is tunneling, and it is also known as encapsulation. So tunneling is a technique in which one protocol is encapsulated in the header of another protocol. It means we are encapsulating IPv4 into the IPv6 address, or if we have to communicate in the IPv4 infrastructure, then the IPv6 address is encapsulated in the IPv4 address. So this is done to make the smooth transition of packet from infrastructure of another protocol. So the component of tunneling process are tunnel management, encapsulation at the tunnel entry point, and encapsulation at the tunnel exit point. So the type of tunneling are manually configured tunneling and the automated tunneling. So these like the manually configured tunneling means Here the IPv6 packets are encapsulated in IPv4 packet, and this is done to carry out IPv6 packets on IPv4 routing infrastructure. So these are point-to-point tunnel that needs to be configured manually. Whereas automated tunneling of IPv6 over IPv4 means the IPv6 nodes can use different type of addresses such as 624, 6RD or ISATAP addresses to dynamically tunnel IPv6 packets over an IPv4 routing infrastructure. So these are the special type of IPv6 unicast addresses that can be used in some part of IPv6 address field, which can be used to determine the IPv4 address of the destination or tunnel endpoint respectively. Then this diagram shows the transition tunneling technique. That means here is there are two users, user 1 and user 2, that are in IPv6 infrastructure, and they have to communicate together, but in between there exists a IPv4 infrastructure. So user 1 sends IPv6 packet to router A. In this case, router A acts as a tunnel entry point, and it encapsulates the IPv6 packet in an IPv4 header and sent to the router B. And in this case, router B acts as a tunnel exit point. It strips off the IPv4 header and forward the packet to the user 2. So in this way, they communicate with each other by existing in between the IPv4 infrastructure. So this is a tunneling process where we are tunneling the IPv4 infrastructure to communicate to make communication between the two IPv6 users. Next is tunneling. Here IPv6 packet encapsulation steps are like: at entry point of the tunnel, the device will decrement the hop limit value by 1 and then encapsulate incoming packet into the IPv4 header. An encapsulated packet transmitted to the tunnel and fragment IPv4 packet, and here the fragmentation of the IPv4 packet is done if necessary. Next is exit point of the tunnel. Here what happens, it receives the encapsulated packet, checks the source of the packet, and then if the packet is fragmented, it will resemble it at the exit point. And it will remove the IPv4 header and send IPv6 original header to the destination. The next part is header translation. So here in a network, when a transmitter device transmits a packet in IPv6 format and receiver still works at the IPv4 format. It means the one that is sender is using a IPv6 format, whereas the receiver is using a IPv4 format. So here we will use the header translation process. So then the tunneling technique will not work here. So header translation technique is used in which header of the IPv6 packet is converted to an IPv4 packet. So header translation uses the mapped address to translate IPv6 to IPv4 address. So here in this diagram, you can see here we have used the header translation device in between the IPv6 and IPv4 host. So as IPv6 want to send something to the IPv4 host, so here the header translation will convert or map the IPv6 packet into the IPv4 packet. Then there is a process known as NATPT, that stands for Network Address Translation Protocol Translation. So this is process that we are using in IPv6, but NAT is used in IPv4 addresses. So this is protocol translation mechanism done in two direction, and here the static NAT defines in one-to-one mapping from one IP subnet to another IP subnet in each direction. So NATPT binds the addresses in IPv6 network with addresses in the IPv4 network and vice versa. So to provide transparent routing for the packet traversing between the address region. So here the advantage of these are, and device and network can choose any address, either IPv4 address or IPv6 address, and traffic run from any side of the network. So the mapping included destination IP address translation in one direction and a source IP address translation in the opposite direction in the protocol translation mechanism. These are the two directions associated in NATPT, that is the destination IP address translation and the source IP address translation in these two particular directions. So this is all about the NATPT. So this all about the transition of IPv4 address to IPv6 or IPv6 addresses to the IPv4. Thank you. Hello, welcome to the course of IPv6. So today we are going to discuss about the mobile that are based upon the IPv6 addresses. So in this class we will discuss about the mobile IPv6, then its feature and the operations of mobile IPv6. So let's first start with that is what is IPv6. So here the mobile IPv6 is an IETF standard, that is the International Engineering Task Force. So here this allows the mobile devices to move from one network to another and they still maintain the existing connection, means they have the existing IPv6 address that is allotted to the mobile at one time. So it is used to add roaming capability to mobile devices in IPv6 network. So this mobile IPv6 is specified in RFC 3775. So the advantages of this mobile IPv6 is that the mobile devices attached with IPv6 can change their point of attachment to the IPv6 network without changing their IP address. It means the IP address of the mobile devices remains same. If they change their point of attachment, it means if they roam in the network from one network to another, the IP address of the mobile will remain same. So here the mobile IPv6 is mainly targeted for the mobile devices such as mobile phones or our laptops. So these are the devices to which the mobile IPv6 is targeting. Next, the need of mobile IPv6. So here the need of mobile IPv6 is due to here we have to attain the mobility for mobile devices. So to attain the mobility for the mobile devices, we need the mobile IPv6. So here the connection to the mobile IPv6 nodes are made with a specific address and it cannot be changed, and these addresses are assigned automatically without user interaction, and the address that is assigned to the mobile devices remain the same in whole network. So it is always assigned to the mobile node and through which the mobile node is always reachable. So this is also maintaining the reachability of the mobile devices as they are assigned to the specific address. So there is no need for the other devices to search for their another IP address as they have the specific addresses. So two type of addresses are assigned to mobile devices. The one is home address and the another one is the care of address. So here the home address is the global unicast address that is assigned to a mobile node, and it is a permanent address and it is remain with the mobile devices as long as they are staying in the network. So and the care of address, that is a global unicast address that is used for the mobile nodes while it is away from the home. So whenever the mobile device is away from its network or home, then a care of address, that is a global unicast address, is assigned to the mobile device. So these are the two type of addresses that we are assigning to the mobile devices: home address and care of address. So let's discuss about few terms that are related to mobile IPv6. So first term is home subnet prefix. So here the home subnet prefix is correspond to a mobile node's home address. So here it correspond to the mobile node in which home address in which it is existing. Home link, here the home link is the link on which a mobile node home subnet prefix is defined. Here the home links define that in which area the mobile device is residing, and we judge about the area from its subnet prefix. And mobile node is a node that can change its point of attachment from one link to another while still being reachable via its home addresses. It means here the mobile node will make the if it change the attachment from one link to the another, but it will remain reachable with its home address. And correspondence node is a node to which the mobile devices is communicating. Home agent is a router on a mobile node's home link. So these are the routers that are present over to the mobile node's home link that are known as home agents. Foreign subnet prefix, here any IP subnet prefix other than the mobile node's home subnet prefix that are known as the foreign subnet prefix. Then is foreign link. Foreign links are the link any link other than the mobile node's home link. So that are the foreign links. So there are home links, foreign links, whereas home subnet prefix as well as the foreign subnet prefix. Then is registration. Here the mobile node send a binding update to its home agent, that is the router in the home network, or a correspondence node for the registration. So to make the connection between the correspondence node, the mobile device sends the registration. That is here the correspondence node may be either mobile or stationary. Then is binding. Binding is the association of home address of mobile node with a care of address. So as the mobile node is start communicating and the network, so it's want the care of address. So here binding is a process in which the home mobile device is associated with its care of address as well. Then is return routability procedure. So this is a procedure that is authorized registration by the use of a cryptographic key exchange. So this is a process in which the authorized registration is done by using the cryptographic key exchange. So these are the few terms associated with mobile IPv6. Next we will discuss about the use of IPv6 feature. So mobile IPv6 use the features of IPv6 such as first one is address auto configuration. It means the addresses are assigned automatically to the mobile devices. So here both type of auto configuration are used, such as stateless, that is network prefix plus the interface ID, and the stateful auto configuration prefix stateful auto configuration that is done with the help of DHCP version 6 server. And the another one is the neighbor discovery. Here the neighbor discovery allow performing the following steps, like how each other presence is discovered, or how to find the router, or how each other link's layer address are determined, and the how to maintain the reachability information. So these all work is done by the neighbor discovery process in IPv6, and mobile IPv6 use this IPv6 feature. Then is extension header. Here the extension header is also used, which provides routing header for route optimization and destination option header. So these are the features of IPv6 that we are using in mobile IPv6 as well. Next is working of mobile IPv6 or the operation. Here the when mobile node is within the home link. So when it is residing in its home link, then the home address is the IPv6 address of the mobile node. So the home address is known as the IPv6 address of mobile node when it is in the home link. So as long as the mobile node is at home, it receives packet through regular IP routing mechanism. It means the destination or the other devices are sending the other devices are sending the packets to the mobile nodes using the home address as it is in its home network. But when the mobile node is away from the home, or it is in a foreign link network, then what happens, it will link to a care of address. It means now it also have the one another address that is known as care of address. So it receives the care of address through regular IPv6 mechanism such as SLAAC, that is stateless address auto configuration, or with the help of DHCP version 6 when connected to the new link. So here it uses the care of addresses. So the other devices, if they want to communicate with the mobile node that is in the another network, they will use the care of address to link with the mobile node. Next we will discuss about the proxy mobile IPv6. So here proxy mobile IPv6 is the only network based mobility management protocol that is standardized by the International Engineering Task Force, and it is specified in RFC 5213. So it is a protocol for building a common and assist technology that is independent of the mobile core network. So here we are designing a network that is independent from the mobile core network. So it accommodates various SS technologies, that is WiMAX, or the 3GPP, that is third generation partnership project or third generation partnership project version 2, and the WLAN, that is wireless local area network based access architecture. So we are using these technologies and the architecture to make this proxy mobile IPv6 exist in the network. So this is all about the mobile IPv6. Thank you.